For centuries, our understanding of planets was limited to the familiar worlds of our solar system. But as our telescopes peer deeper into space, we're uncovering a cosmos far stranger than we ever imagined. Join us as we explore the most extraordinary and unsettling planets ever discovered in our universe. The planet HD 189733b has a mesmerizing blue hue, a stark contrast to the vivid storms that rage across its atmosphere. This striking color is primarily due to the presence of silicate particles in its thick cloud cover, which scatter light in a way that produces a blue appearance, somewhat akin to how Earth's atmosphere influences its sky color. However, this stunning visual is deceptive, as the planet endures some of the most violent weather conditions known outside our solar system. The weather on HD 189733b is nothing short of catastrophic. The atmosphere is characterized by raging winds that can reach speeds exceeding 2,000 miles per hour. These high-velocity winds carry clouds of silicate, creating a hostile environment where rain does not fall as droplets but rather as glassy shards. The intense heat from the nearby star also contributes to the extreme conditions, resulting in temperatures soaring to over 2,000 degrees Fahrenheit on the day side of the planet. This combination of high temperatures, thick clouds, and blistering winds makes HD 189733b a brutal world. Not only is the surface exposed to relentless storms, but the extreme pressure and high temperatures create a scenario where conditions can change dramatically within a short period. Scientists believe that the interaction of the planet's rapid rotation and the fierce atmospheric dynamics contributes to this chaotic weather system. The vivid blue color of HD 189733b represents a captivating yet ominous aspect of this exoplanet. While many might imagine a serene atmosphere, the reality is that these brilliant colors mask a violent environment, revealing the complexity and unpredictability of planetary atmospheres beyond our own. The winds on HD 189733b reach mind-boggling speeds that can exceed 2,000 miles per hour. These winds are not only fast, but also carry extreme heat, creating an atmospheric environment that can reach temperatures of around 2,000 degrees Fahrenheit. To put this into perspective, these conditions are not just hazardous, they are catastrophic by any standard. On Earth, the strongest recorded winds, such as those found in tornadoes or hurricanes, can reach speeds of about 200 miles per hour at their peak. This means that the winds on HD 189733b are 10 times faster than Earth's most extreme storms. While a powerful tornado may unleash destruction in a matter of moments, the winds on HD 189733b are relentless and all-consuming, continuously battering the planet's surface. The intensity of these winds is compounded by the proximity of HD 189733b to its host star, resulting in an atmosphere that is highly charged and dynamic. Furthermore, the heat carried by these winds creates an environment where silicate particles are suspended in the atmosphere. These particles contribute to the planet's haunting blue appearance while also adding to the relentless storms. Unlike Earth's storms, which can bring rain and thunder, the high temperatures and extreme conditions on HD 189733b lead to a different type of precipitation. Instead of water, sharp silicate glass rain falls, further painting a picture of a truly inhospitable world. In contrast, Earth's storms, while fierce and capable of causing tremendous damage, operate under a framework of temperatures and pressures that allow for life to thrive. The apocalyptic nature of HD 189733b offers a stark reminder of just how varied and extreme planetary weather can be in the universe, serving as a point of fascination for scientists who study these distant worlds. The so-called glass rain on HD 189733b is primarily composed of silicate particles, which are formed from the planet's unique atmospheric conditions. The extreme heat on the planet causes these silicates to exist in a gaseous state, which then condense as the atmosphere cools in the upper layers. The intense winds carry these particles, and as they are propelled through the planet's turbulent atmosphere, they eventually coalesce and fall back toward the surface. This precipitation is a result of the planet's harsh weather patterns, where temperatures can vary dramatically between the day and night sides. On the day side, the relentless exposure to the nearby star generates extreme heat, while the night side experiences significant cooling. This drastic temperature shift facilitates the condensation of gaseous silicate, creating the potential for rain. However, instead of liquid water droplets, the atmosphere cools enough for these particles to condense into small, glass-like shards. As these silicate shards fall, they can potentially reach the planet's surface as razor-sharp grains, making the concept of rain quite terrifying. The formation of glass rain illustrates how life-sustaining and destructive processes can coexist, highlighting the stark differences between HD 189733b and planets like Earth. The unusual composition not only informs scientists about the extreme conditions present on this exoplanet, but also challenges our understanding of what constitutes weather and precipitation beyond our own planetary experiences. Ultimately, glass rain serves as a vivid reminder that the universe is full of unique and extreme environments. It encourages curiosity and exploration as scientists unravel the complex meteorological phenomena occurring in far-off corners of our galaxy. The study of such alien weather patterns broadens our understanding of planetary atmospheres and the potential for life in diverse environments, even those as inhospitable as HD 189733b. The glass rain on HD 189733b would pose an immediate and lethal threat to an unprotected human body. As the silicate shards descend through the intense atmosphere, they would be propelled at incredible speeds due to the planet's violent winds. Even a single shard, striking with such force, could cause devastating injuries. With the temperature on the planet reaching incredibly high levels, any exposed skin would suffer severe burns, compounding the danger beyond just the physical impact of the glass. Exposure to this unique form of precipitation would lead to injuries that are not only traumatic but also potentially fatal. The shards, while minute, would act like sharp projectiles, cutting through flesh and organs, leading to deep lacerations and extensive internal damage. The combination of high velocity and sharpness creates a scenario that no protective clothing or gear could effectively withstand. The nature of this rain makes it akin to being caught in a hailstorm of glass rather than a gentle falling rain. Furthermore, the hostile environment of HD 189733b proves to be critical. The intense heat combined with the brutal winds creates a scenario where survival for an unprotected human is impossible. Breathing would become difficult as the atmosphere is not conducive to human life, and the presence of silicate particles could cause further respiratory issues if inhaled. The concept of glass rain serves as a stark reminder of the extreme and inhospitable conditions existing on some exoplanets. It highlights the fine line between what we consider livable and unlivable environments in the cosmos. While it captures our imagination, it also emphasizes the challenges humanity would face as we explore and understand the diversity of planetary systems beyond our own. The atmosphere of HD 189733b is a fascinating yet perilous environment, marked by extreme volatility driven by several interconnected factors. Chief among these is the planet's proximity to its host star, which contributes to high temperatures sufficient to create significant thermal energy in the atmosphere. This intense heat drives the dynamic weather systems that characterize the planet, leading to turbulence and chaotic wind patterns. One of the key contributors to the volatility is the rapid rotation of HD 189733b. The planet completes one rotation in merely a day, which leads to dramatic differences in temperature between its day and night sides. The day side, directly facing the star, experiences blistering heat, while the night side cools significantly. This sharp temperature differential establishes intense pressure systems that fuel extreme winds, creating an atmosphere that's in constant turmoil. The presence of cloud formations rich in silicate particles adds another level of danger. These particles not only contribute to the planet's distinctive blue hue, but are also responsible for the infamous glass rain. When conditions change rapidly, the silicate can condense and be thrust downward by winds at tremendous speeds. The combination of fierce winds and precipitation made of sharp, glass-like shards creates an environment that is fundamentally hostile, even to advanced technologies that might be used for exploration. Furthermore, the atmosphere contains high-energy processes that can produce complex chemical reactions, contributing to a brutal and unpredictable climate. The constant churn of the atmosphere, with its intense storms and shifting patterns, creates a scenario where any attempt at exploration must contend not only with severe temperature fluctuations and hazardous materials, but also with the high likelihood of violent, fast-changing weather conditions. This cocktail of factors establishes HD 189733b as one of the most dangerous planets known, showcasing the extremes of atmospheric dynamics beyond our own world. HD 189733b orbits extremely close to its host star, leading to dramatic and extreme environmental conditions. This proximity results in a staggering amount of energy being funneled onto the planet, generating intense heat on the dayside, where temperatures soar to around 2,000 degrees Fahrenheit. Such thermal input creates a stark contrast between the blazing dayside and the significantly cooler night side, establishing a vicious cycle of weather patterns and pressure systems. Being tidally locked, meaning that one side of the planet always faces the star while the other remains in perpetual darkness, the dayside becomes a baking expanse where the relentless heat can fuel dramatic atmospheric phenomena. This extreme heating leads to rapid thermal expansion of gases, causing violent winds to whip across the surface at speeds that defy typical planetary weather. The energy from the star not only heats the atmosphere, but also provides the dynamic forces necessary for the formation of clouds that contain silicate particles. The culmination of these factors creates powerful storms that continuously churn through the atmosphere. The constant influx of heat means that air near the surface is always trying to rise and disperse, causing turbulence and chaotic flow patterns. As a result, these turbulent conditions drive the vicious winds that can exceed 2,000 miles per hour. The incredibly high winds work in tandem with the intense heat to create an overall atmosphere that is both unstable and dangerous. The proximity of HD 189733b to its star is the catalyst for its extraordinary and menacing weather systems. The direct and overwhelming energy from the star causes an intricate interplay of heat, wind, and pressure variances, leading to an atmosphere that is perpetually in flux. This dance of energy and atmospheric dynamics transforms the planet into a relentless and hostile environment, showcasing the potential extremes of solar influences on planetary conditions in the universe. From the surface of HD 189733b during a glass rainstorm, the sky would present an astonishing yet unsettling spectacle. With the planet perpetually facing its star on one side, this illuminated area would glow with a brilliant bluish light, refracted through the thick clouds laden with silicate particles. The atmosphere would be a swirl of deep blues and vibrant hues, painted with an array of shifting, shadowy formations as storm clouds churn above. As the glass rain begins to fall, the sheer violence of the storm would be evident. The precipitation, composed of sharp silicate shards, would create a dazzling but treacherous display as it cascades from the tumultuous clouds. Instead of a soft, drizzly rain one might experience on Earth, the glass rain would create a chaotic dance of glimmering fragments, reflecting the ambient light around them as they plummet to the surface at lethal speeds. Visibility would likely be limited due to the heavy cloud cover and the intensity of the storm. Alongside the violent winds sweeping across the landscape, any windows to the sky would be filled with a thick, billowing mist of silicates, refracting light in fascinating patterns but also concealing the broader cosmos beyond. The powerful winds would whip the shards around, making the atmosphere appear almost alive, as if the very sky were a swirling vortex of danger and beauty. Even amid the stunning visual display, The underlying terror of the environment would be palpable. The sharp potential for injury would loom large, as the glimmering shards of glass rain would signify an inhospitable world. Instead of cozy storms that bring nourishing rain, the sky above HD 189733b would pulse with a vivid threat, reflecting the hostile and volatile conditions characterizing this alien planet. Studying distant and hostile planets like HD 189733b involves a variety of innovative techniques and advanced technologies, allowing scientists to gather data despite the immense challenges posed by such extreme environments. One of the primary methods for this type of research is through the use of space telescopes that can analyze the light emitted or reflected by these distant worlds. Instruments such as the Hubble Space Telescope and the upcoming James Webb Space Telescope employ spectroscopy, which breaks down light into its component wavelengths, revealing key information about a planet's atmosphere. By observing how a planet passes in front of its star, scientists can measure the light that filters through the atmosphere during a transit. This allows them to detect the presence of various molecules and particles, informing researchers about the planet's atmospheric composition, temperature, and even cloud structures. The unique signature of silicates in the atmosphere of HD 189733b, for instance, can be identified through this method, providing insights into the presence of glass rain and the dynamics of the environment. Numerical models and simulations also play a crucial role in understanding exoplanets. Researchers use complex computer models to simulate the extreme conditions and atmospheric dynamics of these distant worlds. By inputting data gathered from observations and existing knowledge of atmospheric physics, scientists can predict weather patterns, temperatures, and potential weather phenomena, allowing for a comprehensive understanding of what these alien environments might be like. Collaboration across various fields of science further enhances the quality of research. Astronomers, atmospheric scientists, and planetary scientists often work together to share findings, hypotheses, and methodologies. This interdisciplinary approach allows for a more nuanced understanding of distant planets, linking observations to theories about planetary formation, habitability, and the diversity of conditions in the universe. Ultimately, by combining observational data, advanced modeling, and collaborative efforts, scientists continue to expand our understanding of how life and planetary systems function across the cosmos, even in the most extreme environments like HD 189733b. HD 189733b serves as a prime example for understanding the formation and evolution of hot Jupiters, a class of exoplanets characterized by their massive sizes and close proximity to their parent stars. This particular planet provides crucial insights into a range of processes that govern the development of such gas giants. One significant aspect is the theory of planetary migration, which posits that these giant planets originally form further from their stars before moving inward to their current positions. Observations of HD 189733b reveal key features, such as its rapid orbit and extreme atmospheric conditions, that deepen our comprehension of how hot Jupiters interact with their environments. Studies suggest that internal heating from the close proximity to the star plays a significant role in shaping the planet's atmosphere and weather patterns. By examining planets like HD 189733b, scientists can learn more about the factors that influence atmospheric dynamics, including heat distribution and chemical composition, critical for understanding the life cycles of similar gas giants. Moreover, the discovery of silicate clouds and glass rain on HD 189733b also sheds light on the complex chemistry that emerges under extreme conditions. This challenges our existing models of planetary atmospheres and encourages researchers to explore how different elements and compounds interact in high-temperature environments. Such findings may eventually lead to broader implications for atmospheric science on exoplanets. HD 189733b acts as a testing ground for theories about the formation and evolution of gas giants across the universe. By comparing its properties with those of other known exoplanets, astronomers can build a more detailed picture of the diversity of planetary systems and the processes that govern them. Ultimately, studying planets like HD 189733b helps refine our models and enhances our understanding of the complex dynamics involved in the formation of hot Jupiters and the ongoing evolution of planetary systems. Establishing a protected base on HD 189733b would pose an array of unique and formidable challenges due to the planet's extreme and hostile environment. The first and most significant issue would be the intense atmospheric conditions. The winds on HD 189733b can exceed 2,000 miles per hour, which would require any base to be exceptionally durable and resilient. Structures would need to withstand not only the relentless force of these winds, but also the severe impacts from the glass rain composed of silicate shards, presenting an urgent need for advanced materials designed to absorb and deflect these projectiles safely. Additionally, the temperature extremes on the planet present another critical challenge. With surface temperatures easily reaching around 2,000 degrees Fahrenheit, significant engineering solutions would be required to provide effective thermal insulation and temperature regulation within the base. Life support systems would need to operate under these conditions, ensuring a stable environment for human occupants. Such systems would involve not only maintaining breathable air, but also dealing with the potential for chemical reactions that might occur in the heated atmosphere. Radiation would also pose a severe risk due to the lack of a protective magnetic field on HD 189733b. This absence leaves any exposed structures vulnerable to harmful radiation from the nearby star, necessitating the incorporation of robust shielding in the architecture of the base. Engineers would have to carefully calculate the amount and type of protective materials required to safeguard inhabitants against these immense radiation levels. Finally, logistical challenges would arise regarding resource management. Transporting equipment, supplies, and personnel to such a distant world would be a massive undertaking. The need for a self-sustaining base equipped with the ability to extract resources from the hostile environment would be paramount. Technologies for generating power, recycling water, and producing food on site would be essential to create a viable long-term habitat. Together, these challenges underscore that establishing a base on HD 189733b would require monumental technological advancements and innovative solutions to ensure the safety and survival of its human inhabitants. WASP-12b orbits extremely close to its parent star, with a distance of just about 1 million miles. To put this into perspective, this is roughly 1/8 of the distance between Earth and the Sun. This tight orbit results in a year that lasts only for about 1 day, meaning WASP-12b completes a full revolution around its star in an astonishingly short time. The proximity to its star has profound effects on the planet's characteristics and conditions. Due to this close distance, the planet experiences intense stellar radiation, leading to extreme temperatures on its surface that can exceed 2,000 degrees Fahrenheit. Such high temperatures contribute to an atmosphere that is likely in a state of constant volatility, rich in gaseous molecules that would not exist under cooler conditions. Moreover, the gravitational forces at play create tidal interactions between WASP-12b and its star, resulting in significant deformation of the planet. This phenomenon causes the planet to have an oblate shape, meaning it bulges at the equator due to the immense tidal pull. Such deformation influences the planet's internal dynamics and contributes to an overall unstable atmosphere. Additionally, the extreme heat and pressure conditions lead to fantastic atmospheric phenomena, including the potential for loss of atmosphere over time. The intense stellar winds can strip away outer layers, impacting the overall evolution of WASP-12b as it continues its orbit. Observations indicate that the planet may be losing material into space, a process driven by the differential heating and the gravitational interaction with its star, providing crucial insights into how planets close to their stars can evolve and change over time. WASP-12b possesses an unusual oblate shape, meaning it is noticeably flattened at the poles and bulging at the equator. This distortion arises primarily from the extreme gravitational forces exerted by its parent star due to the planet's exceptionally close orbit. With a distance of only about 1 million miles from the star, the gravitational pull is immense, creating significant tidal forces that deform the planet's structure. This oblate shape is not typical among planets and highlights the influence of tidal interactions in close orbit scenarios. On many planets, gravitational forces tend to create a more spherical shape. However, WASP-12b's intense proximity to its star leads to such powerful tidal forces that they effectively stretch the planet outward around its equator, causing the pronounced bulging that distinguishes it from other exoplanets. The effects of this deformation extend beyond mere shape. They can influence the planet's internal dynamics as well. The tidal heating generated by these gravitational interactions contributes to elevated surface temperatures, which can reach extreme levels, allowing for complex atmospheric behaviors. This ongoing distortion plays a role in maintaining the planet's dynamic atmosphere, where high temperatures lead to atmospheric loss and other phenomena that further separate it from typical planetary behavior. WASP-12. B's unusual shape and the processes that give rise to it illustrate the complexities of planetary formation and evolution, particularly for those that venture into close orbits. The characteristics of such exoplanets provide valuable insights into the tidal forces at play in the cosmos, enriching our understanding of the diverse array of planetary systems that exist throughout the universe. WASP-12b is experiencing an extraordinary rate of atmospheric loss due to its extreme proximity to its parent star. Research indicates that the planet is losing material at a staggering rate, equivalent to approximately 100 million tons of atmosphere each year. This intense loss is primarily driven by the intense stellar radiation and gravitational forces that strip away the planet's outer atmospheric layers. As for how long WASP-12b can withstand this onslaught, projections suggest that it may only have a few million years left before it is completely consumed by its star. This timeline is remarkably short in astronomical terms, indicating that the planet is on a rapid decline. Ultimately, as the atmospheric loss continues, it is expected that WASP-12b will be significantly altered or even fully destroyed, likely becoming an unrecognizable remnant of its former self. This rapid consumption serves as a powerful example of the extreme dynamics at play for planets in close proximity to their stars. The process of atmospheric stripping reveals the vulnerabilities of such planets and offers critical insights into the life cycles of those that endure these hostile environments. Observations of WASP-12b help astronomers understand not just the fate of this particular exoplanet, but the broader implications for similar worlds across the universe. Through continued study, scientists hope to learn more about the factors that govern the evolution of planets subjected to such extreme conditions. From the surface of WASP-12b, the sky would present an otherworldly and vibrant spectacle, impacted heavily by the planet's intense proximity to its parent star. With the star looming not far above the horizon, its glow would dominate the sky, casting an intense light that could create a surreal atmosphere. Depending on the time of day, the star might appear as a blinding orb, possibly accompanied by a spectrum of colors ranging from brilliant whites and yellows to deep oranges due to refraction. The atmosphere itself would likely be thick and dynamic, filled with clouds of various gases, likely influenced by the extreme heat and rapid winds. These conditions might lead to frequent storms that could shift the appearance of the sky dramatically within short periods. The swirling gases could create complex cloud formations tinged with hues of blue and red, owing to chemical reactions occurring in the high-temperature environment. Given the tremendous heat of roughly 2,000 degrees Fahrenheit, the atmosphere may also glow with a faint luminescence, enhancing the visual impact of the sky. This would not only create a captivating view, but also a potentially dangerous one, as the intense stellar radiation adds elements of uncertainty to any exploration while rendering the surface inhospitable for human life. Opinions about the visibility of distant stars in this atmosphere would be limited due to the dense cloud cover and the overwhelming brightness of the parent star. Observing the night sky would be quite a rare experience. Once the star set, seeing much beyond the shrouded clouds or atmospheric phenomena would be challenging. The overall effect would be a breathtaking yet hostile environment, striking a juxtaposition of beauty and danger, offering profound insight into the extreme conditions that characterize close-in exoplanets like WASP-12b. Striking a juxtaposition of beauty and danger, offering profound insight into the extreme conditions that characterize close-in exoplanets like WASP-12b. WASP-12b is an exoplanet that orbits extremely close to its host star, resulting in scorching surface temperatures. The average temperature on its surface is estimated to reach around 2,500 degrees Celsius, which is roughly 4,500 degrees Fahrenheit. This intense heat makes it one of the hottest exoplanets ever discovered. At such elevated temperatures, most materials found on Earth would not exist in their solid or liquid states. Instead, they would be vaporized. For instance, metals such as iron and copper would rapidly transform into gas, leaving behind a barren landscape without traditional solid forms. Even elements like lead, which has a relatively high melting point, would be in vapor form on the surface of WASP-12b. Furthermore, this extreme environment leads to unusual atmospheric phenomena. The planet's atmosphere is likely composed of a mixture of exotic gases, including sodium and potassium, which can exist only in gaseous states at these temperatures. This unique composition contributes to the planet's eerie glow as it reflects the light from its nearby star. The conditions on WASP-12b highlight the extreme diversity of planetary environments in our universe, offering a fascinating glimpse into how different factors, such as proximity to a star and atmospheric composition, can dramatically alter a planet's characteristics. WASP-12b has a fascinating composition that combines various elements, primarily characterized by a dense atmosphere containing gases like hydrogen, helium, sodium, and other volatile compounds. This unusual mix gives the planet some unique properties, particularly due to its proximity to its star, which leads to intense heating and extreme weather patterns. As WASP-12b orbits its host star, it is in a constant state of change. The planet is gradually losing its outer layers due to the immense gravitational pull and radiation from the star. The intense heat causes the atmosphere to dissipate, with lighter elements escaping into space. This process is facilitated by the intense stellar winds and radiation that ionize the atmosphere, pushing away atoms and molecules. As a result, the composition of WASP-12b is becoming increasingly depleted and altered over time. In addition to losing its gaseous layers, the planet's surface is likely undergoing transformation as well. The extreme temperatures can lead to the vaporization of heavier molecules, leaving behind a less dense and more unstable environment. Researchers are particularly interested in the fate of these materials, as understanding them can offer insights into the long-term evolution of hot Jupiter-type exoplanets. WASP-12b serves as a living laboratory for studying the dynamics of planetary atmospheres under extreme conditions. Each observation helps scientists piece together the complex interactions between a planet and its star, revealing how such environments evolve and what potential consequences arise for the materials that once made up the planet. The gravitational pull from a star has a significant influence on the atmosphere of a planet like WASP-12b. As this exoplanet orbits so close to its host star, the gravity imposes strong tidal forces that can stretch and distort the planet's shape. This stretching creates an intense gravitational gradient, causing atmospheric particles to experience varying forces depending on their distance from the star. The result of this gravitational interaction is that lighter gases within the atmosphere are more likely to escape into space. When these gases reach speeds sufficient to overcome the gravitational pull of the planet, they become lost to the surrounding void. This process is known as atmospheric escape, and is particularly pronounced in hot Jupiter-type planets that orbit very close to their stars, where extreme heating further facilitates this loss. Additionally, the star's gravity can indirectly affect the temperature of the atmosphere as well. The intense heat from the star not only raises the temperature of the gases present, but also can lead to the ionization of atoms and molecules. This ionized state, combined with the stellar radiation pressure, pushes atmospheric materials even further away, accelerating the rate of loss. The intricate dance between a star's gravitational pull and a planet's atmosphere vividly illustrates how celestial mechanics can frame the evolution of planetary bodies over time. For WASP-12b, this tug-of-war is crucial in determining how much of its atmosphere remains intact and how its composition evolves under the relentless forces exerted by its distant sun. Studying WASP-12b offers valuable insights into the life cycle of planets, particularly those located in close orbits around their stars, known as hot Jupiters. As an example of extreme planetary environments, WASP-12b allows scientists to explore how proximity to a star influences a planet's atmospheric composition, thermal dynamics, and even its eventual fate over time. One of the key aspects researchers investigate is atmospheric escape. By observing how materials are lost from WASP-12b's atmosphere due to the gravitational pull and intense radiation from its host star, scientists can better understand the life cycle of atmospheres on similar exoplanets. This knowledge helps in predicting how other bodies might evolve, especially during their early formation stages when they are still subject to significant external forces. Additionally, the conditions on WASP-12b provide a glimpse into the processes that determine whether a planet can maintain its atmosphere for an extended period. Analyzing the chemical composition of the planet as it loses its gases gives clues about how planets evolve from their formation through various stages, including the possible transition into atmosphereless planets, which are more akin to Mercury or the Moon. WASP-12b's unique environment and its ongoing interactions with its star present a microcosm of planetary evolution. By examining how such planets change over time, scientists can develop models that apply to a broader range of planetary systems, enhancing our understanding of not just this particular world, but also the diverse array of planetary life cycles throughout the universe. If a spacecraft could successfully endure the extreme heat of WASP-12b, it would encounter a turbulent and dynamic upper atmosphere that is quite different from anything found on Earth. This atmosphere is filled with a mix of high-energy gases, including hydrogen, helium, sodium, and various ionized elements. These gases are present due to the intense temperatures that can exceed 2,500 degrees Celsius, allowing many materials to exist in a vaporized state. As the spacecraft penetrates into the upper atmosphere, it would likely encounter varying pressure and density levels. The atmosphere on WASP-12b is not uniform. Instead, it consists of layers that are constantly shifting due to thermal dynamics and interactions with the star's radiation. This creates turbulent wind patterns that could significantly affect the spacecraft's trajectory, posing challenges for navigation and stability. The spacecraft might also detect unusual chemical reactions in the atmosphere caused by the stellar radiation. For instance, elements like sodium and potassium, which are prevalent, can create bright trails that glow as they absorb and re-emit stellar light. The intense radiation can lead to the formation of energized particles, producing a spectacular array of colors and giving the atmosphere an otherworldly appearance. Additionally, the atmosphere may contain clouds or condensation of metal vapors, as higher density materials that are usually solid or liquid on Earth can remain suspended in gaseous form due to the extreme heat. Observing these phenomena could provide scientists with groundbreaking insights into the atmospheric processes occurring in environments far beyond our solar system, enhancing our understanding of planetary atmospheres in extreme conditions. The fate of WASP-12b starkly contrasts with the projected future of our own solar system, highlighting the diverse outcomes for planets based on their specific conditions. WASP-12b, due to its close orbit around a very hot star, is gradually losing its atmosphere, as it is consumed by stellar forces. Over time, this dynamic process will likely render the planet barren, stripping it of significant mass and altering its characteristics entirely. In our solar system, Earth and the other planets are subjected to a different set of influences as they orbit the Sun at varying distances. Scientists predict that as the Sun evolves over the next several billion years, it will exhaust its nuclear fuel and expand into a red giant phase. During this expansion, it is expected to engulf the inner planets, potentially including Earth, leading to dramatic changes in their structures and atmospheres. Some outer planets may experience shifts in their orbits due to the mass loss of the Sun as it sheds layers and becomes increasingly unstable. The trajectory of our solar system indicates a more gradual and subtle transformation compared to the rapid atmospheric loss and intense heat experienced by WASP-12b. While the exoplanet is facing immediate physical changes, the planets in our solar system will endure a long-term evolutionary process over eons, allowing for more stable conditions in the interim. However, both scenarios underscore the complex interplay between a planet's proximity to its host star and its ultimate fate. By studying WASP-12b and comparing it to our solar system, researchers can gain deeper insights into planetary evolution and the various paths that celestial bodies can take in the universe. It reinforces the idea that while some planets face imminent destruction, others may persist for billions of years, shaped by the unique characteristics of their host stars. TRES-2b has earned the title of the darkest known planet due to its remarkable ability to absorb an astonishing 97% of the light that hits its surface. This extreme light absorption means that very little light is reflected back into space, making it appear incredibly dark. In fact, its reflectivity is even lower than that of coal or black acrylic paint, creating an eerie and unusual appearance that sets it apart from many other celestial bodies. The darkness of TRES-2b can be attributed to its atmospheric composition, which is believed to contain substances that contribute to its deep black hue. Researchers suspect that the presence of light-absorbing compounds, possibly including metallic clouds and vaporized sodium or potassium, plays a crucial role in this phenomenon. Such a thick and richly colored atmosphere enhances the planet's ability to trap light, resulting in minimal reflection. When compared to other celestial bodies in our solar system, TRES-2b's darkness is striking. For example, while many planets and moons reflect sunlight and display vibrant colors, TRES-2b stands out as an anomaly. Saturn's moon. Titan and other dark bodies in our solar system may appear relatively dark, but none reach the extreme levels of light absorption found on TRES-2b. This level of darkness has astounded astronomers and prompted further investigation into the atmospheric conditions of exoplanets. Studying TRES-2b offers opportunities to understand how different celestial environments evolve and how their compositions can lead to such captivating and unexpected properties. In a universe filled with bright and colorful celestial bodies, TRES-2b serves as a stark reminder of the diversity of planetary characteristics waiting to be discovered. The atmosphere of TRES-2b is intriguing due to its unique composition, which enables it to absorb an extraordinary amount of light. The planet is categorized as a hot Jupiter, meaning it orbits very close to its star, resulting in high temperatures and specific atmospheric conditions. Researchers believe that the atmosphere contains a mix of substances, including molecules that effectively capture light across various wavelengths. One of the primary contributors to the extreme darkness of TRES-2b is the presence of metallic compounds, which are thought to create thick clouds that enhance light absorption. Elements such as sodium and potassium may exist in vapor form in the upper atmosphere, contributing to the planet's ability to trap light. These metallic clouds not only absorb visible light, but also likely extend the atmospheric effects into the infrared spectrum, further diminishing the amount of light that reflects back into space. Additionally, the atmosphere may be rich in carbon with possible compounds such as gaseous carbon monoxide or carbon dioxide, which can also have strong absorption characteristics. The interactions between these components in the atmosphere can cause complex chemical reactions, leading to a layered structure that is particularly effective in capturing incoming light. This combination of metals, carbon-based molecules, and possibly other light-absorbing elements creates an environment that is not merely dark, but has characteristics that challenge our understanding of planetary atmospheres. Studying TRES-2. B's atmospheric composition not only piques interest in this specific exoplanet, but also contributes to the broader knowledge of atmospheric dynamics in extreme environments, revealing the complexity and diversity of worlds outside our solar system. The surface temperature of TRES-2b reaches an astounding level, generally estimated to be around 1,500 degrees Celsius, which is approximately 2,700 degrees Fahrenheit. This extreme heat is primarily a result of the planet's close proximity to its host star, leading to intense heating of the atmosphere and surface. The remarkable darkness of TRES-2b plays a significant role in contributing to its high temperature. Since TRES-2b absorbs about 97% of the light that strikes it, very little is reflected back into space. This high absorption rate means that almost all the energy received from its star is converted into heat, effectively raising the surface temperature. Unlike planets with reflective surfaces, which might cast away significant amounts of incoming energy, TRES-2b retains nearly all of it, exacerbating the effects of its already intense heat from stellar radiation. Moreover, the light-absorbing materials in TRES-2b's atmosphere, such as metallic clouds, not only capture incoming light, but also may trap heat through a greenhouse effect. This phenomenon can further elevate temperatures, creating a thermal environment that is inhospitable and extreme. The combination of these factors ensures that TRES-2b remains one of the hottest exoplanets known, showcasing how a planet's atmospheric characteristics and surface properties intertwine to influence its thermal dynamics. The interplay between the planet's extreme darkness and its surface temperature illustrates just how diverse and complex planetary systems can be. It invites curiosity about the physical processes that govern the thermal behavior of exoplanets within various environments, expanding our understanding of the cosmos. Standing on the surface of TRES-2b would be a surreal and challenging experience due to its extreme conditions. The temperature would be incredibly high, possibly around 1,500 degrees Celsius, making it akin to being in an immense furnace. This intense heat would render any human unprotected and unable to survive without advanced technology. A specialized heat-resistant suit would be essential for even a brief visit to such an inhospitable environment. The atmosphere would add another layer of complexity. It is thick with light-absorbing materials, primarily composed of metallic compounds and vaporized elements that prevent sunlight from illuminating the surroundings. Instead of the bright light we experience on Earth, the environment would be dominated by deep shadows and an eerie darkness. You would not see the glaring sun directly, as much of its light would be absorbed rather than reflected. This means that visibility would be extraordinarily limited, with only faint muted colors and minimal illumination, contrasting sharply with the vibrant vistas seen on our home planet. Human vision would be significantly affected in such an environment. The lack of reflected light would make it difficult to discern shapes and details, straining one's ability to navigate and perceive the surroundings. While our eyes are adapted to varying light conditions, the near-total darkness would make it comparable to trying to see in pitch blackness, forcing the need for artificial light sources to illuminate the area. Such devices would struggle against the overwhelming absorption characteristics of the atmosphere, making clear visibility even more elusive. Overall, what it would be like to stand on TRES-2b paints a picture of severe heat, incredible darkness, and a landscape that challenges human perception. It is a reminder of the extreme diversity of exoplanetary environments, where the conditions are not just different, but can be radically outside of what is familiar to us on Earth. Measuring the reflectivity of distant exoplanets like TRES 2b involves sophisticated techniques and advanced technology. Scientists primarily rely on a method known as transit photometry. During a transit, a planet passes in front of its host star from our line of sight, partially blocking the starlight. This event causes a temporary dip in the observed brightness of the star, allowing scientists to measure how much light is obstructed. By analyzing the light curve created during a transit, researchers can determine various properties of the planet, including its size and the amount of light it reflects, which is often described as its albedo. The albedo is a measure of reflectivity, representing the fraction of incoming light that is reflected back into space. A low albedo indicates a darker surface, like that of TRES 2b, which absorbs almost all of the light that hits it. In addition to transit methods, scientists also utilize spectroscopy to gather more detailed information about an exoplanet's atmosphere. When starlight passes through a planet's atmosphere during a transit, some wavelengths are absorbed by the gases present. Analyzing the spectrum of the transmitted light allows scientists to identify the specific atmospheric components and their interactions with light, giving insights into the planet's characteristics, including its reflective properties. Moreover, ground-based and space telescopes observe exoplanets indirectly, examining them in various wavelengths of light to detect changes in brightness. These observations can help reinforce findings obtained from transit data and refine measurements of a planet's reflectivity, temperature, and atmospheric composition. By employing these techniques in tandem, scientists can construct a comprehensive understanding of an exoplanet's physical properties, despite the vast distances separating us, illuminating the remarkable diversity of worlds beyond our solar system. TRES 2b serves as a remarkable case study in understanding the diversity of planetary atmospheres beyond our solar system. Its unique characteristics, including its exceedingly high temperature and extreme darkness, highlight how differing conditions can lead to a wide array of atmospheric compositions and behaviors. By examining TRES 2b, scientists can glean insights into the mechanisms that influence atmospheric dynamics on exoplanets. One of the primary lessons from TRES 2b is the role of proximity to a host star. Its tight orbit around a hot star subjects it to intense thermal energy, shaping its atmosphere in ways that differ significantly from planets farther away. The extreme temperatures contribute to processes like atmospheric escape, where lighter gases are lost to space. This illustrates how a planet's position within its star's habitable zone or proximity to its star can drastically alter its atmospheric evolution and stability over time. Additionally, the presence of light-absorbing compounds in TRES 2b's atmosphere helps scientists understand how different materials can affect reflectivity and heat retention. The metallic clouds and chemical interactions contribute to its extraordinary ability to absorb light, resulting in a deeper comprehension of how the composition of an atmosphere can influence a planet's thermal properties and overall climate. This knowledge can then be used to inform models for predicting the atmospheric conditions of other exoplanets with similar characteristics. TRES 2b also emphasizes the importance of studying atmospheres in terms of their diversity. By comparing its unique features with those of other exoplanets that may exhibit very different atmospheric traits, such as those with thick gaseous envelopes or those with significant cloud cover, scientists can develop a broader understanding of planetary formation and evolution. This diversity of atmospheres showcases not only the variety of planetary systems in the universe, but also the complexity of the factors driving these conditions. The study of TRES 2b contributes to the broader quest of astrobiology and planetary science, helping researchers develop more comprehensive models that can apply to the multitude of exoplanets being discovered. Its findings deepen our understanding of how unique atmospheric phenomena can influence the habitability and environmental conditions of planets in distant systems. TRES-2b orbits its host star at an exceptionally close distance, which plays a critical role in shaping its dark nature. This proximity means that the planet is subjected to intense stellar radiation and heat, which significantly impacts its atmospheric composition and behavior. The high temperatures associated with such a close orbit lead to the atmospheric conditions that contribute to TRES-2b's extraordinary ability to absorb light. Due to its tight orbit, TRES-2b experiences extreme heating, which raises temperatures to about 1,500 degrees Celsius. This intense heat can promote the vaporization of various elements and compounds in the atmosphere, resulting in the formation of thick layers of clouds containing metallic compounds. These clouds are particularly efficient at absorbing the incoming light from the star, reinforcing the planet's dark characteristics. Essentially, the extreme thermal environment allows these absorbing materials to flourish, leading to a predominance of darkness over reflectivity. Furthermore, the planet's orbit ensures that it faces its star at all times. Because of this tidally locked nature, one side perpetually receives high levels of radiation, while the other side is shrouded in shadow. Such a configuration can enhance the heat absorption on the sunlit side, contributing to complex atmospheric phenomena that may increase overall light absorption and further reduce reflective qualities when observed as a global average. This relationship between the orbit and the atmospheric conditions highlights how the positioning of a planet around its star can dictate not only temperature and energy dynamics, but also fundamental properties like reflectivity. TRES-2b exemplifies how close orbits not only shape planetary atmospheres, but also contribute to diverse and unexpected physical characteristics seen in planets throughout the universe. The weather patterns on a planet as dark as TRES-2b would be quite intriguing and different from what we experience on Earth. Given its extreme temperatures and the unique properties of its atmosphere, one could expect to see fascinating and possibly chaotic atmospheric phenomena. With a surface temperature reaching about 1,500 degrees Celsius, the climate would be dominated by heat-driven processes. Due to the intense heat absorbed by the planet's atmosphere, one likely weather pattern would be the presence of powerful winds. As sections of the atmosphere heat up significantly, they would expand and rise, creating zones of low pressure. The constant influx of heat from the star could lead to very strong convective currents, generating fierce winds that could sweep across the planet's surface. These dynamic movements might affect the distribution of any cloud formations, potentially resulting in chaotic and rapid shifts in weather conditions. TRES-2b, with its metallic and possibly vaporized materials in the atmosphere, could also experience unusual precipitation phenomena. While typical rainfall as seen on Earth would not be present, one could speculate about the potential for metallic droplets to form and condense under varying thermal conditions. This could lead to a form of rain composed of vaporized metals, although this would likely be a highly hostile and extreme form of precipitation, further emphasizing the unique atmospheric dynamics at play. The orbital configuration of TRES-2b being tidally locked adds another layer of complexity. One side, perpetually facing the star, would experience consistently high temperatures, potentially leading to less stable conditions and frequent atmospheric upheavals. In contrast, the dark side, which experiences no direct sunlight, could become significantly cooler, affecting how the atmosphere circulates between these vastly different regions. This complex interplay may give rise to unique and unpredictable weather patterns that challenge our current understanding of meteorology. Overall, the atmospheric dynamics on a planet like TRES-2b would be shaped by its darkness, extreme temperatures, and unique materials present in its atmosphere, leading to weather patterns that are radically different from those of Earth, inviting further curiosity and investigation into such alien environments. The darkness of TRES-2b presents significant challenges for the existence of life forms, should they be able to survive in such extreme conditions. With its atmosphere absorbing nearly all incoming light, One of the most fundamental requirements for life as we know it, energy from the sun, is effectively non-existent on TRES 2b. This absence of natural light would drastically limit the potential for photosynthesis, the primary means by which life on Earth converts sunlight into energy. Without sunlight, any hypothetical life forms would need to rely on alternative energy sources. One possibility is that life might adapt to utilize geothermal energy from the planet's core or chemical energy derived from hydrothermal vents, assuming such features exist in TRES 2b's environment. Extremophiles on Earth, which thrive in extreme conditions such as deep-sea vents or acidic lakes, provide potential analogues for what life on TRES 2b might resemble, but with even more adaptations required to cope with the extreme temperatures and atmospheric conditions. Additionally, the thick and metallic-rich atmosphere might introduce other challenges. High temperatures could lead to an environment that is not only inhospitable due to heat, but also filled with corrosive chemicals. Life forms living in such an atmosphere would need to develop robust protective mechanisms to withstand extreme conditions, including resistance to high temperatures and tactile environments laden with gaseous metals. The dynamic weather patterns influenced by the planet's heat and atmospheric composition would also pose hazards. High-velocity winds and possible precipitation of metallic droplets could create an ever-changing and hostile landscape, making it difficult for any life forms to establish stable habitats. While trawling through the possibilities of life on a planet like TRES 2b ignites curiosity, the darkness and hostile conditions would necessitate significant adaptations for any potential organisms to survive. Like Earth's extremophiles, whatever forms might arise would probably be fundamentally different from known terrestrial biology, thriving on alternative energy sources and exhibiting unique survival mechanisms to endure their harsh, dark environment. Navigating and studying a dark planet presents a unique array of challenges for space exploration. One of the most pressing issues is the lack of natural light, which can hinder visibility and complicate imaging processes. Instruments that rely on sunlight or other light sources for observation may struggle to function effectively, requiring spacecraft to be equipped with specialized technology designed to operate in low-light conditions. For example, infrared sensors become crucial as they can detect heat emitted from the planet, revealing important geological features that might otherwise remain hidden in darkness. Communication is another significant hurdle when exploring a dark planet. Without the benefits of light to help relay signals, radio waves might take longer to travel to and from the planet. This increased distance would enhance the delay in data transmission, creating challenges in real-time monitoring and decision-making for missions. Moreover, if the planet possesses a dense atmosphere or is surrounded by debris, these obstacles could further disrupt communication efforts. Studying the planet's surface also demands creative solutions. Rovers and landers must be able to traverse rugged terrains often shrouded in shadow, which demands robust engineering and advanced navigation systems. Any sample collection or surface analysis would need to be conducted using instruments that can function optimally in low-light environments, perhaps utilizing autonomous systems to ensure successful operation without continuous human oversight. Finally, understanding the environmental conditions of a dark planet, such as extreme temperatures and possible atmospheric composition, is critical. Researchers would need to develop protective measures for spacecraft, ensuring they can withstand not only the cold of perpetual darkness, but also the potential atmospheric pressure and chemical composition. These countless factors underscore the complexity and ingenuity required for successful missions to explore such mysterious worlds. Kourou 7b is a fascinating exoplanet that has captured the attention of astronomers due to its extreme conditions. It is classified as a hot super-Earth, which means it is larger than Earth but smaller than Neptune. Its proximity to its host star results in an incredibly high surface temperature, likely exceeding 1,000 degrees Celsius. This intense heat causes rocks and minerals on the planet's surface to undergo a state of melting, creating a landscape that can be compared to a molten lava ocean. As Corot 7b is tidally locked with its star, one side constantly faces the heat, while the other remains in perpetual darkness. This results in an extreme temperature gradient between the two sides, contributing to dynamic atmospheric conditions. The continually heated side of the planet may have large expanses of molten rock that flow much like a lava ocean. This state of affairs could lead to active volcanic processes, with lava flows and possibly even eruptive events shaping the surface. That's right. Furthermore, the planet's composition plays a pivotal role in its lava-like appearance. If Corot 7b consists mainly of silicate materials, much like Earth, then the melting of these substances at high temperatures would lead to a blistering, churning surface. Spectroscopic studies suggest the presence of silicate minerals, reinforcing the idea that its landscape resembles that of an ocean of lava due to ongoing geological activity and extreme thermal conditions. Scientists are particularly intrigued by Corot 7b because studying such a planet helps us understand the formation and evolution of rocky exoplanets. Investigating the dynamics of its surface not only sheds light on its nature, but also broadens our knowledge of planetary systems beyond our own. Corot 7b is situated in a remarkably close orbit around its host star, located approximately 3 times closer than Mercury is to the Sun. This proximity places the planet in an environment where it experiences intense levels of stellar radiation and heat. Being so close means that Corot 7b completes a full orbit around its star in less than 1 day, leading to significant thermal extremes that result in its extreme surface conditions. The high influx of energy from its star causes Corot 7b to reach scorching surface temperatures that can exceed 1,000 degrees Celsius. This relentless heat is responsible for the ongoing melting of rocky materials on its surface, creating what resembles a lava ocean. Additionally, the tidal effects caused by the close gravitational interaction with its star lead to a phenomenon known as tidal locking. As a result, one side of Corot 7b is permanently exposed to sunlight, while the other side remains in darkness, exacerbating the temperature differential and influencing its atmospheric dynamics. The extreme conditions not only shape the physical landscape but also affect the planet's potential for atmospheric retention. High temperatures can lead to atmospheric loss, as lighter elements may escape into space. This gives rise to the possibility that Corot 7b lacks a substantial atmosphere, further exposing its surface to the harsh conditions of its stellar environment. Thus, its proximity to the star is a key factor in creating the unique and extreme characteristics observed on this intriguing exoplanet. The temperature difference between the day and night sides of Corot 7b is astounding, with estimates suggesting that the disparity can reach up to 1,000 degrees Celsius. On the day side, which is perpetually exposed to the intense heat of the star, temperatures soar to around 1,000 degrees Celsius or higher. In stark contrast, the night side, encased in darkness, can plummet to much lower temperatures, potentially dipping to around 0 degrees Celsius or even colder. This extreme temperature gradient is primarily a result of Corot 7b's tidal locking to its star, meaning that one hemisphere of the planet always faces the star while the other remains in eternal darkness. Such a configuration leads to a very different thermal environment across its surface, where the side basking in sunlight continuously absorbs heat, while the dark side lacks this energetic input. As a result, the day side becomes scorching hot, and the night side remains frigid by comparison. These vast temperature differences create dynamic atmospheric conditions that could lead to high winds and potential weather systems as heat attempts to equilibrate across the planet. Understanding this temperature variation provides insights into how planets in extreme environments behave, contributing to our knowledge of planetary climates beyond our solar system. This research can also illuminate the possibilities for atmospheric retention or loss, further informing scientists about the nature of exoplanetary environments like that of Corot 7b. The extreme heat on Corot 7b has a profound impact on the composition and dynamics of its atmosphere. With surface temperatures exceeding 1000 degrees Celsius, the thermal energy is sufficient to strip away lighter atmospheric components. Hydrogen and helium, which are common in many celestial atmospheres, would likely be the first to dissociate and escape into space due to the intense thermal conditions. This loss of lighter gases can leave the planet with a significantly different atmospheric makeup compared to what we might observe on cooler terrestrial planets. Additionally, the extreme heat encourages the presence of heavier molecules such as silicates and metals in vapor form. As rocks and minerals on the surface melt, they can release gaseous constituents that further alter the atmospheric composition. These molten materials can contribute to a rich inventory of elements and compounds, although the overall pressure and density of such an atmosphere are likely to be quite low. This is in stark contrast to a more stable atmosphere found on planets like Earth, where lighter elements can be retained due to lower temperatures and gravity. The relentless daytime heating further creates conditions for potential atmospheric dynamics. Powerful temperature gradients can lead to strong winds as the atmosphere attempts to redistribute heat from the scorching day side to the cooler night side. Such circulation patterns could contribute to weather phenomena, although any atmosphere present on Corot 7b is expected to be tenuous and not comparable to our own. Understanding how extreme temperatures influence the atmospheric composition on Corot 7b enhances our grasp of how different exoplanets can evolve under harsh conditions. It also provides valuable insights into the potential for habitability and atmospheric retention on rocky planets orbiting close to their stars. A human or spacecraft attempting to land on the surface of Corot 7b would face severe and potentially catastrophic challenges due to the planet's extreme environment. Firstly, the staggering surface temperatures, which can exceed 1000 degrees Celsius, would be incinerating for human beings without specialized protective gear, far beyond what any current spacesuit is designed to withstand. The heat would also pose significant challenges for any spacecraft, likely causing severe structural damage to materials and components that are not engineered to endure such high temperatures. If an unprotected human or an inadequately shielded spacecraft managed to reach the surface, the intense heat would lead to immediate combustion of materials and rapid bodily harm. The high temperatures could trigger failures in navigation, communication systems, and other essential electronics on a spacecraft, making any potential landing mission impossible. Moreover, the potential lack of a substantial atmosphere on Corot 7b would contribute to an absence of aerodynamic forces, removing traditional landing profiles that rely on air resistance to slow descent. Even for spacecraft designed specifically for extreme environments, robust thermal protection and advanced cooling systems would be paramount. Engineers would need to incorporate materials capable of withstanding such heat for the duration of a landing attempt and beyond, all while ensuring that critical systems could still function under harsh conditions. The challenges do not end with landing. Once on the surface, a craft would also contend with possible volcanic activity or lava flows, further complicating surface operations. A human or spacecraft landing on Corot 7b would encounter an environment that is inhospitable and dangerous, demanding unprecedented technological advancements and an understanding of extreme planetary conditions. An exploration of this nature serves as a humbling reminder of the limits of current space exploration technology, while highlighting the challenges posed by distant and extreme worlds in our universe. The intense tidal forces exerted by the star on Corot 7b play a significant role in shaping its geology. As a tidally locked planet, one side constantly faces the star, leading to a tremendous gravitational interaction that can create internal stresses within the planet. These tidal forces can generate heat through a process known as tidal heating, where the deformation of the planet's shape due to gravitational pull causes friction within its interior. This friction generates substantial amounts of heat, contributing to the already high surface temperatures observed on Corot 7b. As a result of tidal heating, the geology of Corot 7b could be dynamic and active. The continuous heating can lead to the melting of subsurface rock and the possible presence of magma pockets. This activity can result in volcanic processes on the planet's surface, where molten rock can erupt, flow, or create large lava plains. Such volcanism not only reshapes the landscape, but can also contribute to the atmospheric composition by releasing gases and materials into the thin atmosphere, influencing overall environmental conditions. Furthermore, the extreme tidal forces also contribute to the planet's unique temperature distribution, with one side experiencing unrelenting exposure to the star, while the other remains in cold darkness. This stark thermal contrast can create geological features along the terminator line, the boundary where day meets night, where the interaction of varying temperatures could lead to unique weathering processes, or even the formation of specialized geological structures. Overall, the tidal forces from the star are crucial in driving Corot 7b's geological activity. They maintain the high internal temperatures necessary for volcanic activity and shape the planet's surface through dynamic processes, highlighting the intricate relationships between celestial mechanics and geology found in exoplanetary systems. Understanding these forces enhances our knowledge of how planets evolve in extreme environments and the potential for diverse geological features throughout the universe. Studying lava planets like Corot 7b offers valuable insights into the processes of planetary formation and evolution. One significant aspect we can learn involves the conditions that lead to the formation of terrestrial planets. The extreme environments found on lava planets provide a unique perspective on how planetary bodies develop under high temperatures and pressure, which may also apply to early Earth and other rocky planets in formation. The presence of molten surfaces on these planets suggests that they underwent intense heating, likely due to their proximity to their host stars. Analyzing such conditions helps scientists understand the role of stellar radiation and gravitational forces in shaping a planet's evolution. For instance, it provides context for the types of materials available during the planet's formation and how the compositions might vary based on their orbit and the characteristics of the star they orbit. This knowledge aids in the development of models that describe the conditions necessary for different types of planetary bodies. Furthermore, studying the geological processes occurring on lava planets can shed light on how volatile elements and compounds behave in extreme environments. Understanding how these elements are released or retained in high-energy conditions helps contextualize the potential for habitability on planets that might be more temperate but share similar compositional traits. If these processes were replicated elsewhere in the universe, they could inform scientists of the likelihood of finding Earth-like planets that could support life. Finally, the study of lava planets emphasizes the variety of planetary types that exist beyond our solar system. They challenge our definitions of habitability and put forth new scenarios of planetary systems that may differ drastically from our own. By exploring the extremes, scientists gain a broader view of planetary formation, leading to a compendium of knowledge that highlights the remarkable diversity and complexity of worlds in our universe. Determining the composition of planets like Corot 7b, which boast extreme surface conditions, requires the use of innovative techniques and advanced technology. One primary method is through remote sensing, where scientists analyze the light emitted or reflected from the planet. Spectroscopy plays a crucial role in this process, allowing researchers to observe the spectrum of light that interacts with the planet's surface and atmosphere. Different materials absorb and emit light at characteristic wavelengths, providing valuable clues about the composition of surface rocks and minerals. Even in the face of high temperatures, infrared spectroscopy can be employed effectively. As heat causes certain materials to emit infrared radiation, scientists can detect these emissions to identify the presence of silicate metals and other chemical compounds. Instruments aboard telescopes, such as those on space observatories, can gather this spectral data from a distance, enabling researchers to infer a planet's composition without the need for direct measurement. Another approach involves analyzing the gravitational interactions between the planet and its host star. By observing the effect of Corot 7b's gravity on starlight, the wobble it induces in its star, scientists can estimate the planet's mass and density. These factors provide additional information regarding its composition. A higher density might suggest a rocky or metallic core, whereas a lower density could imply a gaseous or less dense structure. Finally, scientists can also rely on models of planetary formation and evolution in extreme environments to draw conclusions about the likely composition based on observed physical characteristics and behaviors. By combining observational data with theoretical models, a more comprehensive picture of a planet like Corot 7b emerges. This blended approach enables researchers to piece together the mystery of a planet's makeup, even when faced with the challenges imposed by its harsh surface conditions. The sky viewed from the surface of Corot 7b would be an extraordinary sight, shaped by its unique environment and proximity to its host star. With one side of the planet perpetually facing the star, the day side would experience unrelenting illumination, creating a dazzlingly bright sky dominated by the intense light of the star. The atmosphere, if present, would likely scatter this light, potentially bathing the surroundings in a harsh, blinding brilliance that could flood the landscape with an unyielding glare. Contrasting with the blazing brightness on the day side, the night side of the planet would present a stark, dark sky, dotted with stars. As the night side remains in perpetual darkness, the absence of sunlight would make it an ideal vantage point for stargazing, revealing countless distant stars and cosmic phenomena. However, the extremely high temperatures on the day side might limit the presence of a thick atmosphere, leading to a thin and hazy sky that would slightly dim celestial visibility. If there were volcanic or geological activity, it could produce a hazy atmosphere filled with ash and gas particles. This could create vibrant colors during twilight and dramatically affect the skyline during those rare moments near the terminator line, where day meets night. Chi, if Corot 7b had an atmosphere rich in various gases released by volcanic activity, the sky could display different shades depending on the composition of the atmosphere, possibly introducing greens, reds, or yellows into the view. Overall, the experience of looking up from the surface of Corot 7b would be unlike anything on Earth, characterized by extreme brightness and dynamic atmospheric conditions, reflecting the planet's unique stance in its orbital relationship with its star. Each shift in position would offer fascinating perspectives on the universe, influenced by the interplay between heat, light, and geological processes, elements that define this extraordinary world. Over time, the extreme conditions on Corot 7b are expected to undergo gradual yet significant changes, influenced primarily by its close proximity to its host star and the dynamics of planetary evolution. One of the critical aspects affecting its future is the relationship between the planet and its star, which drives tidal forces that lead to continual heating. As these forces evolve, they could modify the planet's geological activity and surface conditions. For instance, tidal heating may initially promote volcanic processes that shape the planet's landscape, but over time, as the planet cools and loses its internal heat, the level of geological activity may diminish significantly. An important consequence of Corot 7b's ongoing exposure to high temperatures is the gradual loss of its atmosphere, assuming it possesses one. Constant exposure to intense stellar radiation can strip lighter elements from the atmosphere, especially those at the highest energy states. Over time, if the atmospheric loss continues unchecked, this could leave Corot 7b with a diminished or even negligible atmosphere, fundamentally altering its surface conditions and potentially exposing more of the rocky landscape beneath. The fate of Corot 7b may ultimately involve an extended cooling phase as it exhausts its internal heat. With volcanic activity decreasing and an atmosphere thinning, the planet could transition towards a more stable geological state. In the long run, if Corot 7b were to encounter significant enough atmospheric loss, it could resemble other airless bodies in our solar system, such as the Moon or Mercury, characterized by a stark, barren landscape. Thus, Kuro 7b's extreme conditions, largely dictated by its proximity to the host star and the interplay of tidal forces, are likely to change over time from an active molten landscape with geological activity to a more stable, cooler environment. This evolution highlights the intricate and ever-changing nature of planets under extreme conditions, providing valuable insights into the life cycle of exoplanets and their potential variations throughout the cosmos. PSRB 1257 plus 12b is often referred to as a zombie planet due to its unusual characteristics and the peculiar circumstances of its formation. This exoplanet orbits a pulsar, a highly magnetized, rotating neutron star that emits beams of radiation. Unlike typical planets that form around regular stars, PSRB 1257 plus 12b is situated in a system where the host star has already undergone a cataclysmic death. The pulsar was once a massive star that exploded in a supernova, leaving behind a dense core that emits radiation as it spins. The fact that a planet can exist in such a harsh environment, long after the host star's life cycle has ended, is what has earned it the nickname Zombie Planet. The existence of PSRB 1257 plus 12b raises intriguing questions about planetary formation and survival in extreme conditions. When the pulsar formed from its progenitor stars collapse, it is believed that any surrounding material would have been subjected to intense radiation and strong gravitational forces. Despite this, PSRB 1257 plus 12b managed to survive, which suggests that it may have formed earlier and was resilient enough to endure the catastrophic events that led to the creation of the pulsar. This leads to the hypothesis that some planets can be formed from residual material after a star has died, rather than solely from a circumstellar disk that exists around a living star. Additionally, PSRB 1257 plus 12b's orbit around a pulsar means it experiences extreme conditions unlike those of Earth or even many other known exoplanets. The planet is bombarded by high levels of radiation which can significantly impact its atmosphere and surface conditions. This extreme environment makes it unlikely that life as we know it could exist there, contrasting sharply with the ideal conditions of planets orbiting sun-like stars. The peculiar nature of PSRB 1257 plus 12b challenges traditional notions of planetary systems and prompts scientists to rethink the ways planets can form and persist even after the violent death of their stars. This zombie planet serves as a fascinating example of resilience in the universe and inspires further exploration into the diversity of planetary environments across cosmic landscapes. A pulsar is a highly magnetized, rotating neutron star that emits beams of radiation out from its magnetic poles. These pulsars are formed as the remnants of massive stars that have exhausted their nuclear fuel and undergone a supernova explosion. During this cataclysmic event, the core of the star collapses under its own gravity, compressing protons and electrons to form neutrons, resulting in an incredibly dense object. This collapse transforms the star into a neutron star, and if the conditions are right, it can become a pulsar. The key difference between a pulsar and a normal star lies in the pulsar's behavior and physical properties. Normal stars, like our Sun, generate energy through nuclear fusion, converting hydrogen into helium in their cores while radiating light and heat. They are in a stable balance between gravitational forces trying to collapse the star and the outward pressure from nuclear fusion. In contrast, a pulsar no longer undergoes fusion and instead rotates rapidly, often several times per second or more, due to the conservation of angular momentum from the original star. Pulsars are known for their remarkable rotation and the beams of radiation they emit, which can sweep across space like a lighthouse beam as the star spins. When the beam points toward Earth, we detect a pulse of radiation, creating the characteristic pulsing effect. This pulsation can be incredibly regular, allowing scientists to use pulsars as precise cosmic clocks. In fact, some pulsars are so consistent in their emission that they can be used to test theories of gravity and measure time across astronomical distances. Overall, while a normal star undergoes fusion in a stable state, a pulsar is the remnants of a star that has ended its fusion processes, becoming a rapidly rotating, highly magnetized neutron star characterized by its unique emission of radiation and extreme physical conditions. The survival of PSR B1257 plus 12b during the supernova event that created its host pulsar is a fascinating occurrence that challenges conventional understandings of planetary formation and stability. When the pulsar was formed, it resulted from the collapse of a massive star that went through the supernova phase. During such an explosion, most of the outer material of the star is expelled into space, creating a turbulent environment filled with high-energy radiation and intense shock waves. One hypothesis for how PSR B1257 plus 12b survived this cataclysm revolves around its formation and location. It is possible that the planet formed from residual material left over from the protoplanetary disk surrounding the progenitor star before it went supernova. This context implies that PSR B1257 plus 12b may have been embedded in material that was not directly affected by the force of the explosive event, allowing it to remain intact. Another possibility is that the planet was able to endure the supernova's aftermath due to its particular distance from the progenitor star. If PSR B1257 plus 12b was located far enough away, the explosive energy would not have been sufficient to disrupt or destroy it entirely. This distance would allow the planet to withstand the ejected material and radiation typically associated with supernova events. Moreover, the dense conditions created by the supernova might have even contributed to the planet's current orbit around the pulsar. As the outer layers of the progenitor star were expelled, the gravitational influence shifted. If PSR B1257 plus 12b was already orbiting the star at the time, it could have adjusted its orbit to settle into a stable position around the newly formed pulsar. Ultimately, the survival of PSR B1257 plus 12b is a testament to the resilience of planetary bodies and underscores the complexity of planetary systems. This unusual scenario opens up intriguing questions about planetary formation processes in the violent environments of evolving stars, providing a deeper understanding of how planets can persist through extreme cosmic events. PSR B1257 plus 12b is exposed to highly intense levels of radiation due to its proximity to its host pulsar. As a pulsar, PSR B1257 plus 12 emits beams of electromagnetic radiation across a range of wavelengths, including radio waves, X-rays, and gamma rays. This radiation results from the pulsar's rapid rotation and strong magnetic field, which accelerate charged particles to incredibly high energies. As these particles move along the magnetic field lines, they produce powerful emissions that can be detected across vast distances. The intensity of the radiation that PSR B1257 plus 12b encounters is significantly higher than what we experience on Earth. The environment around pulsars can bombard the planet with energetic particles and radiation capable of damaging or even stripping away atmospheres. The radiation levels present in such an environment can pose extreme challenges for any potential habitability, effectively rendering the planet inhospitable to life as we know it. Moreover, the radiation emitted by PSR B1257 plus 12b's host pulsar can create intense environments that could affect the planet's surface and any atmosphere it might possess. The energy from the pulsar can lead to heating of the surface and may result in the loss of lighter atmospheric components, further altering the planet's characteristics. Prolonged exposure to such harsh radiation could erode or eliminate an atmosphere, affecting the planet's ability to retain any volatile materials. This high-energy environment exemplifies the extremes of cosmic conditions and highlights the unusual nature of planets orbiting pulsars. Studying these radioactive interactions not only enhances our understanding of the dynamics of planetary formation around such stellar remnants, but also informs our broader knowledge of the environmental conditions present in diverse exoplanetary systems, cautioning us about the potential challenges of habitability in various cosmic contexts. The proximity of a planet to a pulsar influences its physical characteristics in several significant ways. Pulsars emit beams of intense electromagnetic radiation, primarily in the form of radio waves, and these beams can bombard any nearby celestial bodies with immense energy. When a planet orbits close to a pulsar, its surface can experience extreme radiation levels, leading to intense heating and, in some cases, atmospheric stripping. For instance, the gravitational and magnetic forces of a pulsar are incredibly strong. This can affect the planet's geological structure, potentially causing tectonic activity or altering its surface composition. Additionally, the intense electromagnetic radiation can lead to remarkable phenomena such as auroras that would far exceed anything seen on Earth. These auroral displays can result from charged particles from the pulsar interacting with the planet's magnetic field. Moreover, the distance from the pulsar influences the planet's potential for habitability. A close orbit may render it inhospitable, as high radiation doses can damage any biological organisms present. However, if a planet is located within a specific distance known as the habitable zone, conditions could allow for some form of life to exist despite the pulsar radiation, provided there are local protective mechanisms in place. Interestingly, pulsars can also strip away a planet's atmosphere if it is too close. The relentless barrage of high-energy particles can erode atmospheric layers over time, leaving a barren world. Thus, the characteristics of planets orbiting these enigmatic remnants of massive stars are defined largely by their proximity to the pulsar, making them fascinating subjects of study in astrophysics. Standing on the surface of PSR B 1257+12b, a planet orbiting a pulsar, the sky would be a striking sight. The pulsar itself, an incredibly dense neutron star, would dominate the heavens, glowing brightly as it beams electromagnetic radiation across the cosmos. Since pulsars rotate rapidly, these beams sweep through space like lighthouse signals, creating a pulsating effect in brightness that would seem almost otherworldly against the backdrop of the cosmos. Given the intensity of the radiation emitted by the pulsar, the atmosphere of PSR B 1257+12b, if it has one, would likely present vibrant auroral displays. These natural light shows, resulting from high-energy particles colliding with atmospheric gases, could fill the sky with brilliant hues of green, blue, and even red. The atmosphere would be dramatically different from Earth's, heavily influenced by the pulsar's relentless energy, which could create a surreal and beautiful but hostile environment. The other celestial bodies visible in the sky would also contribute to the stunning scenery. Due to the planet's position, surrounding stars might appear unusually bright and twinkling, as they would not be obscured by pollution or atmospheric distortion of the sort found on Earth. If there are other planets orbiting in the same system, they might be visible, adding to the complex and intricate pattern of light overhead. Nighttime might bring a less defined darkness, as the pulsar constantly emits radiation. Depending on how the planet's rotation aligns with the pulsar's beams, the sky could either be drenched in constant light or experience alternating stark contrasts between brightness and shadow. This dynamic environment would create a sky that is both breathtaking and intimidating, a far cry from our familiar experience on Earth. The regular pulses from a pulsar have a profound impact on a planet's environment, shaping conditions in ways that are both fascinating and extreme. As pulsars emit beams of radiation at regular intervals, these beams can bombard the planet with intense electromagnetic energy. This continual exposure can significantly affect the atmospheric chemistry, particularly if the planet has a thin atmosphere or is located very close to the pulsar. High-energy particles from the pulsar can ionize gases in the atmosphere, leading to unusual chemical reactions. This ionization process may disrupt any potential atmosphere, gradually stripping it away over time. If the atmosphere is sufficiently thin, the intense radiation can expose the surface to harsh conditions that would be hostile to life as we know it. Any water or organic compounds that might reside on the planet could be severely affected, potentially evaporating or breaking down into simpler, unprotected forms. The regular pulses also mean that the planet experiences consistent cycles of radiation exposure. When the pulsar beams are directed at the planet, temperatures could rise dramatically, leading to a scorched surface during these periods. Conversely, during the intervals when the beams are not focused on the planet, surface temperatures might drop significantly. This extreme fluctuation in temperature could create dynamic weather patterns that differ radically from what we see on Earth, further enhancing the environment's variability. Additionally, the radiation from the pulsar can produce spectacular auroral displays as charged particles interact with the planet's magnetic field. These displays would not only manifest visually as vibrant light shows, but could also contribute to further atmospheric alterations through the energy exchanges involved. Thus, the interaction between the pulsar's regular pulses and the planet creates a distinctive environment, one filled with challenges and remarkable phenomena. Studying PSRB 1257 plus 12b offers valuable insights into planetary formation and the potential for survival under extreme conditions. As one of the first extrasolar planets discovered orbiting a pulsar, it serves as a unique case study that challenges traditional concepts of planet formation. The existence of this planet suggests that celestial bodies can emerge from environments that are drastically different from the stellar conditions typically associated with planet formation. The intense radiation environment created by the pulsar demands an adaptation in how we think about planetary atmospheres and surfaces. If PSRB 1257 plus 12b has an atmosphere, the mechanisms it employs to maintain that atmosphere, despite the pulsar's radiation, may reveal how planets can sustain themselves in hostile environments. This could challenge established theories about habitability, expanding our understanding of what conditions might support life elsewhere in the universe. Moreover, the planet's survival over time against the pulsar's relentless bombardment provides insights into the resilience and adaptation of planetary materials. Studying how the composition of PSRB 1257 plus 12b has been affected by radiation and particle influx informs scientists about the processes that govern the longevity and stability of planets exposed to extreme conditions. By examining the geological features and surface compositions, researchers can glean clues about planetary evolution, including how such worlds differ from those in more benign environments. Additionally, this study sheds light on the dynamics of planetary systems around unusual stellar remnants. The mechanisms by which planets are formed and maintained in such a system highlight the diversity of planetary formation processes and underscore the complexity of the universe. Overall, PSRB 1257 plus 12b serves as a critical piece of the puzzle in understanding not only our own solar system, but also the broader cosmos in which a multitude of strange and resilient worlds might exist. Scientists employ a variety of techniques to detect and study planets orbiting pulsars, capitalizing on the unique characteristics of these rapidly rotating neutron stars. One primary method is the observation of changes in the timing of the pulsar's signals, known as pulsar timing. Pulsars emit regular radio waves with remarkable precision, akin to a cosmic clock. If a planet orbits a pulsar, its gravitational influence can induce slight variations in the timing of these pulses. By analyzing these variations, researchers can infer the presence of planetary companions and determine their mass and orbital characteristics. Another method involves looking at the Doppler effect, which manifests as shifts in the frequency of the pulsar's signals. When a planet orbits a pulsar, its gravitational tug can cause the pulsar to wobble slightly, changing the observed frequency of its radiation. This phenomenon can provide vital information about the planet's mass and the shape of its orbit. These subtle effects can be detected with highly sensitive radio telescopes, which are essential for analyzing the faint signals associated with pulsars. Additionally, scientists often use observational techniques like periodic variations in brightness. If the planet passes in front of the pulsar from our line of sight, it can block some of the pulsar's radiation, leading to a temporary decrease in the observed brightness. This transit method helps confirm the planet's presence and contributes to understanding its size and orbital path. Combining results from these varied techniques can yield a comprehensive picture of the planetary systems around pulsars. By studying multiple pulsar candidates, researchers can better understand the prevalence and characteristics of such planets, offering insights into the dynamics of celestial systems shaped by extreme environments. The remarkable interplay of timing, frequency, and brightness creates a rich tapestry of information that allows scientists to explore these fascinating worlds. If life could theoretically exist on PSRB 1257+12b, it would need to develop remarkable adaptations to cope with the extreme radiation emitted by the pulsar. One potential adaptation could be the evolution of highly efficient protective mechanisms, such as thick, layered exoskeletons or shells that can shield living organisms from harmful radiation. Drawing parallels with extremophiles on Earth, organisms might develop biochemical pathways that repair damage caused by radiation exposure, allowing cells to function despite high levels of ionizing radiation. Additionally, life on PSR B 1257+12b might rely on forms of metabolism that are less affected by extreme conditions. For instance, organisms could possess metabolic processes that utilize radiation as an energy source, akin to photosynthesis but optimized for the wavelengths emitted by the pulsar. This unique photosynthetic-like adaptation could allow them to harness energy from the pulsar's beams while mitigating harmful effects. Moreover, any potential life forms would need to be incredibly resilient. They might evolve mechanisms for rapid reproduction and mutation, allowing them to adapt swiftly to changing conditions. Such rapid evolutionary processes could help ensure survival in a landscape where environmental conditions fluctuate dramatically, driven by the pulsar's consistent radiation patterns. Finally, the presence of radiation could also push life to adopt underground or subsurface lifestyles to escape the harshest effects. Subterranean habitats might provide a protective barrier against direct radiation exposure, allowing organisms to thrive in relatively stable environments. Overall, if life were to exist on PSRB 1257+12b, it would likely exhibit a suite of extraordinary adaptations designed to confront the unique challenges posed by its extreme environment. Evidence suggesting that Gliese 1214b might be covered in a global ocean comes from a combination of its size, density, and atmospheric characteristics. This exoplanet, located in the constellation Virgo, is classified as a sub-Neptune, meaning it has a radius larger than Earth but smaller than that of Neptune. Its dimensions indicate that it could possess a substantial amount of water, possibly existing in liquid form, especially considering its equilibrium temperature likely allows for such conditions. One key piece of evidence is the planet's density, which is relatively low when compared to other rocky exoplanets. This lower density implies that Gliese 1214b is likely not composed predominantly of heavy metals or silicate materials. Instead, it suggests that a significant portion of the planet's mass may consist of lighter materials, such as water, which could form a deep ocean covering the planet's surface. Models of exoplanet formation indicate that planets in this size range can retain substantial amounts of water, especially when they are located within the habitable zone of their stars. Observations of Gliese 1214. B's atmosphere have also contributed to the hypothesis of a global ocean. Data collected from transit observations reveal the presence of water vapor in the planet's atmosphere, leading to speculation that a vast ocean could be present beneath the atmosphere. The spectral signatures detected on Gliese 1214b indicate a significant water component, supporting the theory of an oceanic environment. Finally, the planet's distance from its host star suggests it might reside in conditions conducive to maintaining liquid water. Being located within the temperate zone allows for the possibility that temperatures are just right to support oceans, potentially creating an ecosystem below the surface. All these clues point toward the compelling possibility that Gliese 1214b is indeed shrouded in a vast global ocean, making it an intriguing candidate for further study in the search for potentially habitable worlds. The atmosphere of Gliese 1214b differs significantly from that of Earth in several key aspects. One notable distinction is the abundance of water vapor, which is present in much higher concentrations on Gliese 1214b. While Earth's atmosphere contains only a small percentage of water vapor, studies of Gliese 1214b suggest that its atmosphere may be laden with water, providing tantalizing evidence for a potential global ocean beneath the clouds. In addition to water vapor, the atmospheric composition of Gliese 1214b is expected to include a higher proportion of hydrogen and helium. These light gases are common in the atmospheres of sub-Neptune-sized planets and are significantly more prevalent than in Earth's atmosphere, which is primarily composed of nitrogen and oxygen. The presence of these lighter gases can contribute to a thicker, more extended atmosphere on Gliese 1214b, which may influence the planet's climate and weather patterns. Another interesting aspect is the lack of certain gases that characterize Earth's atmosphere, such as carbon dioxide and atmospheric oxygen, in significant amounts. While Earth's atmosphere supports diverse life forms that constantly recycle gases, the atmosphere of Gliese 1214b is likely more influenced by its proximity to its host star and its unique formation history. This may result in a stark contrast in the types of chemical processes that could occur, especially concerning potential habitability. The differing atmospheric pressure and temperature conditions also play a crucial role. Gliese 1214b's atmosphere is expected to have a higher pressure than Earth's due to its thicker composition, which could alter the behavior of gases and affect physical processes such as cloud formation and weather systems. These variations in composition, pressure, and temperature allow for fascinating comparisons between Gliese 1214b and Earth, deepening our understanding of the diversity of planetary atmospheres in the universe. At the bottom of Gliese 1214b's potential ocean, pressure would be significantly higher than what we experience on Earth. The increased pressure comes from the weight of the water above it, and this pressure would grow with depth. Given that Gliese 1214b is a sub-Neptune planet, it is hypothesized to have a thick atmosphere and a potentially deep ocean, giving rise to considerable hydrostatic pressure. To add context, Earth's oceanic pressure increases by approximately 1 atmosphere for every 10 meters of depth. On Gliese 1214b, estimates suggest that its ocean could be several hundred kilometers deep based on observations of its size and potential water content. If we consider the possibility of an ocean reaching depths of 100 kilometers, for example, the pressure at the bottom of such an ocean would be extraordinarily high, potentially around 10,000 atmospheres or more. This extreme pressure would create harsh conditions influencing the physical and chemical properties of water and any potential life forms that might exist there. At such depths, water's behavior would differ significantly from the conditions we are used to on the surface. For organisms, if they were to exist under these conditions, they would need remarkable adaptations to withstand the immense pressure. The environments at great depths on Gliese 1214b would not only challenge the understanding of how life might survive, but also provide insights into the characteristics of high-pressure aquatic environments, guiding scientists in their search for life in extreme conditions across the universe. The pressure at the bottom of Gliese 1214b's vast ocean would be tremendously high, presenting a uniquely challenging environment to study. Gliese 1214b has an equilibrium temperature that can range from approximately 50 to 100 degrees Celsius, depending on factors such as its distance from its host star and the characteristics of its atmosphere. This temperature is conducive to maintaining water in a liquid state, especially given the potential for a deep ocean beneath the surface. However, the state of water would vary with depth due to the influence of pressure and temperature. At shallow depths near the surface, where temperatures may remain close to the equilibrium temperature, water would likely be in liquid form. However, as one descends deeper into the ocean, the temperature would increase due to the geothermal gradient, the natural increase in temperature with depth in a planet's interior. This rising temperature, combined with increasing pressure, creates several diverse states of water under such extreme conditions. In the mid-regions of the ocean, water could still remain liquid, albeit under substantial pressure, which raises the boiling point of water significantly. Water at depths of several kilometers might be under extreme conditions, where despite high temperatures, it remains stable in the liquid form due to this elevated pressure. At greater depths, for instance, in regions that exceed significant pressures, water might transition into a supercritical state. This occurs when water reaches temperatures and pressures beyond its typical liquid or gas phases, blurring the lines between liquid and gas characteristics. At that point, water would not behave like either typical liquid water or steam, but would exhibit properties of both, possibly affecting how any chemical reactions occur in that environment. While Gliese 1214Ba's water might be liquid at shallower depths, deeper regions could see water in a supercritical state as temperature and pressure increase. The intricate balance between these variables presents a fascinating scenario for scientists studying the potential for life in alien ocean worlds. On a planet entirely covered by water, unique weather patterns would emerge, shaped by the interplay of temperature, humidity, and atmospheric conditions. One prominent feature could be the prevalence of constant cloud cover. Without land masses to disrupt airflow, moisture would continuously circulate, leading to a more uniform atmosphere. This could result in significant condensation and the formation of extensive cloud systems, limiting sunlight penetration and creating a rather diffuse lighting effect across the surface. The ocean's vast expanse would likely foster powerful storms, as the warm water serves as an energy source for atmospheric disturbances. In warmer regions, thunderstorms could be common, fueled by the high evaporation rates that generate significant humidity. Tornado-like systems might also develop over warm water, given the right atmospheric conditions leading to intense localized phenomena. Such storms could produce violent weather systems, including heavy rainfall and strong winds, contributing to a dynamic and ever-changing climate. A planet covered entirely in water might also experience unusual thermal stratification. Without terrain to promote variability, the upper layers of the ocean could heat up during the day, while deeper layers remain cooler. This temperature gradient can lead to the formation of ocean currents, which would interact with the atmosphere above. Surface winds could influence ocean dynamics, potentially producing large waves and choppy conditions that reflect changes in wind patterns. Another intriguing possibility is the potential for bioluminescence in the water to play a role in the nighttime environment. If life forms in the ocean produce light, this bioluminescence could create captivating displays after storms or disturbances, illuminating the surface in enchanting patterns. Overall, the absence of land on a water-covered planet would lead to distinctive weather phenomena driven by the unique interactions between the ocean and atmosphere, resulting in an environment that is both extraordinary and complex. Gliese 1214b is significantly larger and more massive than Earth, characterized as a sub-Neptune-type exoplanet. Its radius is approximately 2.5 times that of Earth, and its mass is roughly 7 times greater. This substantial increase in size and mass has important implications for gravity and the overall experience of a human visitor. First and foremost, the stronger gravitational pull on Gliese 1214b would create a heavier environment for someone trying to walk or move around. A human visitor would feel considerably heavier, experiencing an acceleration due to gravity that could be several times that of Earth's. This increased gravity could make normal activities, such as walking or standing, more strenuous and lead to fatigue more quickly. Over time, the body would need to adapt to these new physical demands, potentially affecting muscle strength and cardiovascular health. The larger size and mass of Gliese 1214b also suggest it could have a denser atmosphere than Earth, which would present both challenges and peculiarities for a human visitor. The atmospheric pressure could be significantly higher, depending on the thickness of the atmosphere and the depth of water if there is indeed a global ocean. This higher pressure could lead to complications with breathing, requiring specialized equipment or adaptations to ensure safety. Temperature conditions, alongside atmospheric composition, would also play a critical role in the experience of a human on Gliese 1214b. Depending on the environmental factors present, they may encounter conditions ranging from warm and humid to potentially extreme weather phenomena. The visitor would need to be prepared for a range of temperatures and conditions, possibly requiring advanced technologies or gear designed to withstand fluctuations and ensure comfort. Overall, while the intriguing environment of Gliese 1214b offers exciting prospects for exploration, the substantial differences in size, mass, and gravity would pose significant challenges for human visitors, necessitating careful planning and adaptations for safe and effective exploration. Studying Gliese 1214b provides critical insights into the potential for water-rich planets across the universe. As one of the first sub-Neptune-type exoplanets discovered, its characteristics are instrumental in expanding our understanding of planetary systems that may harbor liquid water. The presence of substantial amounts of water vapor in its atmosphere and the possibility of a global ocean beneath the surface raise compelling questions about the conditions necessary for water to exist in liquid form on other planets. The size and mass of Gliese 1214b suggest that it can retain a thick atmosphere rich in volatile compounds, including water, which challenges traditional views about planetary formation. This indicates that planets with sizes comparable to Gliese 1214b may often accumulate considerable amounts of water during their formation. Observations of this planet encourage researchers to explore the variety of planet types that could exist in the universe, shifting the focus from only Earth-like planets. Additionally, the study of Gliese 1214b allows scientists to investigate the types of processes that lead to the retention of water and atmospheres in different environments. Understanding how this exoplanet behaves under the influence of its host star can shed light on the dynamics of climate systems on water-rich planets, including how factors like stellar radiation and atmospheric composition can create diverse environmental conditions. Exploring this water-rich exoplanet also enhances our knowledge about potential habitability. Water is often considered a prerequisite for life as we know it, making Gliese 1214b a valuable target in the search for extraterrestrial life. By analyzing its atmospheric compositions and environmental conditions, researchers can formulate more refined criteria for identifying planets with the potential for supporting life. Overall, Gliese 1214b serves as a critical benchmark in understanding the existence and characteristics of water-rich planets throughout the cosmos, paving the way for future explorations and discoveries. The absence of land on Gliese. 1214b could significantly influence the potential for life, shaping both ecosystems and evolutionary pathways in unique ways. With a planet entirely covered by water, the dynamics of life would be primarily aquatic, potentially fostering the evolution of diverse marine organisms. This expansive ocean environment could lead to a variety of adaptations tailored to a life spent in water, such as different forms of locomotion, feeding strategies, and reproductive mechanisms. One major impact of a water-only world is the potential for nutrient distribution. In the absence of land, essential minerals and nutrients would have to be sourced from the ocean water itself. Life forms might evolve specialized methods to utilize these resources effectively, relying on the currents and tides to distribute nutrients and energy throughout the aquatic environment. Such adaptations could lead to complex food webs based purely on aquatic dynamics, rather than the land-based ecosystems we observe on Earth. Without terrestrial environments, life on Gliese 1214b would also need to contend with heightened pressure and varying temperatures at different ocean depths, which can determine the types of organisms that can thrive. Whether in the upper layers where sunlight penetrates or in the dark depths, organisms may have to adapt to extreme conditions, leading to unique biological innovations. Bioluminescence, for instance, could become prevalent if life forms evolve in light-deprived portions of the ocean, playing vital roles in communication and predation. Moreover, without land as a habitat, evolutionary pressures would differ from those on Earth. The development of complex land-based organisms requires overcoming challenges posed by gravity, resource competition, and environmental variability associated with terrestrial environments. In contrast, life on Gliese 1214b could lead to more simple organisms or unique aquatic ecosystems, potentially lacking the land-based biodiversity seen on Earth. Overall, while the presence of liquid water might enhance the potential for life, the lack of land would create distinct challenges and opportunities for evolution, leading to a fascinating, albeit fundamentally different, biosphere. From the surface of Gliese 1214b, the sky and horizon would present a unique and possibly stunning sight. Given that the planet appears to be covered entirely by water, the landscape would lack any terrestrial features such as mountains or forests, offering an uninterrupted expanse of ocean. The atmosphere, which might be thicker than Earth's and rich in water vapor, could produce a constantly variable sky, characterized by dense cloud cover that may limit direct sunlight. The colors of the sky could vary significantly depending on the time of day and atmospheric conditions. A thick atmosphere might scatter sunlight differently, leading to hues of soft blues or even shades of green and yellow, reminiscent of a sunlit ocean rather than a clear sky. This atmospheric scattering could create a dim, diffused light that provides an otherworldly glow to the environment. On overcast days, the sky might appear uniformly grey, with clouds potentially swirling and shifting ominously, reflecting the dynamic weather patterns generated by the warmth of the ocean beneath. The horizon could be quite different from what we experience on Earth. Without highlands or elevated landforms to interrupt the view, the horizon would be a smooth, continuous curve where the ocean meets the sky. In the distance, one might witness a gradual blending of colors as the sea transitions into the atmosphere, giving rise to a serene yet surreal visual experience. This expansive view could evoke a sense of openness, while simultaneously stirring curiosity about what lies beyond the limit of sight. Or, if there are any light interactions due to the presence of bioluminescent organisms or reactions within the atmosphere, the sky could occasionally be adorned with captivating displays. Additionally, if Gliese 1214b were located close to its host star, there could be dazzling sunrises and sunsets characterized by vivid colors painting the sky momentarily, making each day an intriguing spectacle. Overall, the sky and horizon from Gliese 1214b would create a distinctly beautiful, puzzling, and exotic atmosphere for any hypothetical visitors. Studying a planet entirely covered in water presents unique challenges and intricacies for scientists. To unravel the mysteries of such a world, researchers employ a combination of remote sensing techniques, advanced technology, and theoretical models. Sending spacecraft equipped with specialized instruments is one of the primary methods. These instruments can measure various characteristics of the planet from afar, including its gravitational field, magnetic field, and thermal emissions. Such data can provide invaluable insights into the planet's underlying structure and composition. For instance, variations in a planet's gravitational field can hint at differences in density beneath the surface, potentially revealing the presence of solid land masses or varying thicknesses of water. Similarly, the analysis of light reflected off a planet's surface can indicate the materials present. Infrared spectroscopy is particularly useful here, as it detects specific wavelengths of light that correspond to different chemical compounds. This method can identify organic molecules and mineral content in the water and potentially on the ocean floor. Further, scientists utilize computer simulations and theoretical modeling to predict and visualize the conditions of these aquatic worlds. These models may incorporate data from similar bodies within our solar system, enabling researchers to understand how tectonics, ocean currents, and even atmospheric conditions can shape a covered planet. By comparing the hypothetical models with data collected from space missions, scientists can refine their understanding of oceanic worlds. Exploring these water-covered planets also engages the use of advanced submersibles or autonomous underwater vehicles for ocean worlds closer to home, such as Europa, one of Jupiter's moons, which is believed to have a subsurface ocean. Although many planets like this exist beyond our reach for direct exploration, the combination of remote sensing, modeling, and theoretical understanding allows scientists to piece together the puzzle of their formation, composition, and potential habitability. Gliese 436b is often referred to as an ice-on-fire planet due to its unique composition and the extreme conditions that exist on its surface. Discovered in 2007, this exoplanet is classified as a hot Neptune, which indicates it has characteristics similar to Neptune but orbits very close to its host star. This proximity subjects the planet to intense heat, leading to unusual physical and chemical phenomena. The description of ice on fire stems from the planet's likely composition, which includes a substantial amount of water ice. However, due to the extreme temperatures reaching up to more than 700 degrees Fahrenheit, this ice exists not as the familiar solid we recognize on Earth, but instead undergoes a transformation into a supercritical fluid. In this state, water's properties are altered, allowing it to exhibit characteristics of both liquid and gas. Under such high pressures and temperatures, the water molecules become highly compressed, creating a scenario where ice can appear to be burning. Another fascinating aspect of Gliese 436b is its atmosphere, which is thought to contain elements such as hydrogen and helium, as well as heavier compounds. The intense thermal environment and pressure contribute to the potential for reactions that could lead to complex atmospheric dynamics. This unique setting allows scientists to explore how high temperatures affect various materials and compounds, emphasizing the bizarre and extreme nature of this exoplanet. The combination of intense heat, high pressure, and unique composition results in this captivating description of ice on fire, illustrating how the universe produces worlds that challenge our understanding of what is possible. The study of Gliese 436b expands our knowledge of planetary systems and the diverse environments that exist throughout the cosmos, inviting continued curiosity and exploration. Hot ice refers to a state of water that exists under extreme pressures and temperatures, such as those found on the exoplanet Gliese 436b. While on Earth we typically think of ice as the solid form of water, the conditions on Gliese 436b are so unique that ice behaves differently. In this context, hot ice describes water that exists as a supercritical fluid where it displays properties between those of a liquid and a gas. On Gliese 436b, with temperatures exceeding 700 degrees Fahrenheit and high atmospheric pressure due to the planet's proximity to its host star, water undergoes dramatic changes. The immense pressure causes the water molecules to be packed closely together, preventing them from transitioning into a gas under the heat. Instead, they remain in a fluid state, but with characteristics more akin to those of a dense liquid, often referred to as supercritical water. This phenomenon occurs because at sufficient temperatures and pressures, the distinctions we make between solid, liquid, and gas begin to blur. Supercritical water can dissolve substances like a liquid, and it can also diffuse through materials like a gas. This dual nature contributes to the idea of hot ice, where water retains the physical structure of ice at high temperatures due to the oppressive conditions on the planet. These extreme conditions provide a fascinating area of study for scientists, as they reveal insights into how water and possibly other compounds behave in environments far different from our own. Understanding the properties of hot ice on Gliese 436b not only helps in characterizing this exoplanet, but also deepens our knowledge of the potential material and geological interactions that could occur elsewhere in the universe, where extreme environments play a crucial role in shaping planetary characteristics. The pressure on Gliese 436b plays a critical role in determining the state of water on its surface. This exoplanet is classified as a hot Neptune, orbiting extremely close to its host star, resulting in high temperatures. Coupled with the significant gravitational force acting upon it, the pressure at the surface of Gliese 436b is extraordinarily high, estimated to be considerably greater than what we experience on Earth. Under such high-pressure conditions, water behaves differently than it does in our familiar environment. On Earth, water transitions between solid, liquid, and gas states based on temperature and atmospheric pressure. However, the extreme pressures on Gliese 436b prevent water from readily evaporating into gas or freezing into solid ice. Instead, the interactions between the water molecules are altered, leading them to exist primarily in a dense supercritical state. In the supercritical state, water exhibits unique properties. It acts like a liquid, capable of dissolving substances and flowing, but lacks the distinct gas-liquid dichotomy we see on Earth. The molecules are packed closely together, which means that even at elevated temperatures, water does not vaporize. This stability results in conditions where hot ice can exist, a term used to describe how water maintains a fluid-like consistency under extreme conditions while exhibiting high temperatures. Moreover, this high pressure can affect chemical reactions and interactions occurring within the water, potentially leading to complex phenomena not seen under standard atmospheric conditions. For instance, the dissolved gases and minerals could create intricate chemical processes, influencing both the atmospheric composition and any potential geological activity on the planet. Overall, the combination of pressure and temperature on Gliese 436b results in a fascinating and complex state of water, compelling scientists to further explore and understand how extreme conditions influence molecular behavior and the physical properties of substances across different planetary environments. Landing on Gliese 436b would present insurmountable challenges for both humans and spacecraft due to the planet's extreme environmental conditions. As a hot Neptune, Gliese 436b is characterized by incredibly high temperatures exceeding 700 degrees Fahrenheit, combined with immense atmospheric pressure far greater than what we experience on Earth. These two factors alone create an environment that is not conducive to human survival or traditional spacecraft functionality. For a human attempting to land on Gliese 436b, the immediate dangers would be extreme heat and pressure. The high temperatures would exceed the tolerable limits for human beings, leading to severe heat-related injuries or death in a matter of minutes. Humans require a stable, breathable atmosphere to survive, and the atmospheric composition of Gliese 436b, likely rich in hydrogen and other gases, would not provide the necessary conditions for respiration. Similarly, any spacecraft designed for landing on Earth or even other celestial bodies would face catastrophic failure upon entering the atmosphere of Gliese 436b. The intense heat generated during the descent would require advanced thermal shielding beyond current engineering capabilities to prevent the spacecraft from melting or burning. Additionally, the enormous atmospheric pressure could crush most conventional vehicles, making them incapable of withstanding such conditions. Even if we were to engineer an advanced spacecraft that could survive the descent, the planet's surface is presumably a thick, gaseous atmosphere rich in supercritical fluids rather than a solid surface. This implies that landing would not occur in the traditional sense as on a terrestrial body. Instead, any attempt to settle on the planet would be akin to sinking into a dense medium, akin to a liquid, making standard landing protocols ineffective. The extreme temperatures, crushing atmospheric pressure, and the likely gaseous or supercritical nature of the planet's surface create insurmountable barriers to human exploration and traditional spacecraft landings. Gliese 436b remains a fascinating object of study in the context of understanding extreme planetary environments, but it presents unique challenges that render it inhospitable for human beings and conventional space travel. Gliese 436b and Neptune share some similarities, but they also exhibit significant differences in size and composition. Both are categorized as Neptune-like planets, yet Gliese 436b is classified as a hot Neptune due to its close proximity to its host star, resulting in much higher surface temperatures. In terms of size, Gliese 436b is slightly smaller than Neptune. Neptune has a diameter of about 30,000 miles, while Gliese 436b boasts a diameter that is about 22,000 miles. This size difference gives Gliese 436b a smaller volume and mass in comparison to Neptune, although it still retains the characteristics associated with gas giants. The composition of the two planets also differs markedly. Neptune's atmosphere is largely composed of hydrogen and helium, with significant amounts of methane contributing to its distinctive blue color. Gliese 436b, while also likely primarily composed of hydrogen and helium, is notable for its high densities, which suggest the presence of heavier elements and compounds. On Gliese 436b, the pressure from its environment can lead to the existence of hot ice or supercritical liquids, which do not exist on Neptune. The temperature and pressure conditions on Gliese 436b are far more extreme than those found on Neptune, leading to unique atmospheric phenomena. While Neptune has a relatively cold atmosphere, typically with temperatures around -300 degrees Fahrenheit, Gliese 436b's proximity to its host star results in vastly higher temperatures, exceeding 700 degrees Fahrenheit. These contrasting conditions lead to fascinating differences in how each planet's atmosphere behaves, influencing cloud formations, wind speeds, and overall weather patterns. Ultimately, while Gliese 436b and Neptune share a classification as gas giants, their differences in size, environment, and composition offer distinct perspectives on the diversity and variability of planetary systems, enhancing our understanding of the range of conditions that can exist across the universe. Studying Gliese 436b provides valuable insights into the behavior of water under extreme conditions, particularly in high-temperature and high-pressure environments. As a hot Neptune, Gliese 436b experiences ambient temperatures that exceed 700 degrees Fahrenheit, alongside atmospheric pressures far greater than those found on Earth. These conditions lead to unique states of water that are not only fascinating, but also essential for understanding the properties and behavior of water as a substance. One of the most significant revelations from Gliese 436b is the concept of supercritical water. Under the combination of high pressure and temperature, water transitions into a supercritical state, where it exhibits properties of both liquid and gas. In this state, water can dissolve various substances and traverse materials similarly to a gas, while still maintaining a dense, flowing quality of a liquid. Investigating how water behaves in this supercritical state on Gliese 436b allows scientists to explore its chemical interactions, solubility characteristics, and the potential for different reactions that could occur in such environments. Additionally, studying the conditions on Gliese 436b can shed light on the stability and structure of water ice at high pressures. Scientists can examine how water transforms into different types of ice under extreme conditions, which could lead to a better understanding of ice's crystalline structures. This knowledge has broader implications for understanding ice on other celestial bodies, particularly those with massive atmospheres or extreme temperatures. Furthermore, as researchers explore water's behavior on Gliese 436b, they can make comparisons with similar conditions potentially existing on other exoplanets or moons in our solar system, such as those found in the outer planets or their moons like Europa or Enceladus. Understanding how water behaves in extreme environments is essential for developing theories about the potential for habitability or the presence of exotic forms of life in these regions. Ultimately, studying Gliese 436b enriches our understanding of water as a fundamental substance. The The findings could lead to advancements in fields ranging from planetary science to materials science, offering insights into not just the behavior of water, but also the physical and chemical processes taking place under extreme conditions across various celestial environments. Scientists employ a variety of techniques to detect and study the unusual properties of Gliese 436b's surface, utilizing both observational astronomy and computer modeling to gain insights into this unique exoplanet. One of the primary methods for studying Gliese 436b, like other exoplanets, is transit photometry. This technique involves monitoring the brightness of a star over time. When Gliese 436b transits, or passes in front of its host star, it causes a slight dimming of the star's light. The magnitude of this dimming provides indirect evidence of the planet's size and can offer insights into its atmosphere and surface conditions. Spectroscopy plays a crucial role in understanding the atmospheric composition of Gliese 436b. When light from the host star passes through the planet's atmosphere during a transit, specific wavelengths are absorbed by molecules present in that atmosphere. By analyzing the spectrum of the starlight, scientists can identify the chemical composition and determine the presence of various elements and compounds. This technique is essential for studying the unusual properties of the planet, particularly since Gliese 436b is thought to have characteristics of supercritical water and other exotic materials. Further exploration of Gliese 436b's surface properties relies on computer simulations and models. Researchers create simulations based on the known physical laws of chemistry and physics to predict how water and other compounds behave under the planet's extreme temperature and pressure conditions. These models aid in understanding how the surface might appear and how materials would interact, providing predictions about the environment, including expected states of water and other elements. Additionally, scientists draw from comparative studies, looking at similar exoplanets and their observed characteristics, as well as studying extreme conditions on Earth and our solar system. This allows researchers to build a more comprehensive picture of what to expect on Gliese 436b based on different settings. While studying this distant world presents challenges, the combination of observational data, advanced modeling, and comparisons with existing knowledge enables scientists to derive valuable insights into the unique properties of Gliese 436b's surface and atmosphere. A planet characterized by hot ice, such as Gliese 436b, would likely have a complex atmosphere shaped by extreme temperatures and pressures. The atmospheric conditions on such a planet would be influenced significantly by its proximity to its host star, leading to high thermal energy and unique chemical compositions. The atmosphere would primarily be composed of hydrogen and helium, similar to other gas giants, but it might also contain heavier elements and compounds due to the high pressure conditions. In particular, the presence of supercritical water, where water exists in a state that exhibits fluid characteristics between a liquid and a gas, could shape the dynamics of the atmosphere significantly. This supercritical state allows for increased solubility of various substances, which could affect chemical interactions and the formation of clouds or other atmospheric phenomena. Given the high temperatures, the atmosphere may also include water vapor in substantial amounts, but under extreme pressure, this vapor would not condense into liquid or solid forms as we know on Earth. Instead, the interactions between different compounds would lead to the formation of complex chemical environments. Various trace gases might be present, including ammonia, methane, or even carbon-based compounds, depending on the planet's particular conditions and elemental availability. Additionally, the extreme energy from the proximity to the host star would influence atmospheric dynamics, likely leading to vigorous weather patterns with high winds and turbulent conditions. The variability in temperature across the planet, caused by its rotation and interactions with the dual state of materials, could result in unique temperature gradients, possibly generating intense storms or other dynamic weather systems. Overall, the atmosphere of a planet with hot ice would combine high temperatures, significant pressure, complex chemical interactions, and dynamic behavior, creating an environment that starkly contrasts with those found on terrestrial planets, or even typical gas giants like Neptune. Studying such atmospheres could yield critical insights into the behavior of materials and the potential for exotic forms of chemistry that differ from what we observe in more familiar environments. Gliese 436b currently maintains a stable state as a hot Neptune, primarily due to its relatively consistent orbit around its host star, which allows for a steady influx of energy. The balance between its gravitational forces and the thermal energy received from its star helps sustain its current atmospheric conditions and the unique properties associated with its surface materials, such as the existence of hot ice. However, while the planet appears stable now, various factors could lead to changes over time. One contributing factor to potential changes in Gliese 436b's state is its proximity to its host star. As a planet orbiting very close to a star, it experiences intense stellar radiation, which affects its atmospheric composition and thermal dynamics. Over extended periods, this continuous exposure could lead to atmospheric erosion, particularly if the star becomes more active or undergoes changes related to its life cycle. In such scenarios, increased stellar activity could strip away significant portions of the atmosphere, altering the pressures and temperatures experienced on the planet. Furthermore, the immense heat and pressures on Gliese 436b could also lead to gradual changes in its material composition. The interaction of heat with its atmospheric components might result in chemical reactions that produce new compounds or alter existing ones. This could affect the overall stability of the atmosphere and the state of materials present on the planet's surface, potentially creating different dynamics over time. Additionally, Gliese 436b's orbital stability should be considered. If there are perturbations caused by gravitational interactions with other celestial bodies or changes in its host star's mass or energy output, the planet's orbit could be affected. Variations in its orbital path might result in shifts in temperature and pressure, leading to further consequences for the atmospheric and surface conditions. While Gliese 436b currently appears stable in its hot Neptune state, various factors, including stellar activity, atmospheric dynamics, and potential orbital changes, could influence its long-term stability. Understanding these dynamics sheds light on the evolutionary processes that affect planets under extreme conditions and helps inform our knowledge of exoplanets in diverse environments across the universe. The extreme conditions present on Gliese 436b, characterized by high temperatures and immense atmospheric pressure, could give rise to various exotic forms of matter. The planet's unique environment allows for the potential existence of substances that challenge our conventional understanding of chemical and physical properties. One notable exotic form of matter is supercritical water. Under the immense pressures and high temperatures on Gliese 436b, water can transition into a supercritical state, where it behaves neither strictly as a liquid nor a gas. In this state, water exhibits remarkable solubility properties, and its interactions with other materials could lead to complex chemical reactions and the formation of unusual compounds. Furthermore, the intense pressure could lead to the formation of dense ice structures not seen in typical conditions. Ice discovered on Gliese 436b might exhibit unique crystalline forms, such as high-pressure ice phases like Ice 7 or Ice X, which occur at conditions far beyond those found on Earth. These forms of ice possess different properties that could significantly affect the planetary geology and atmosphere. Another potential exotic material that might form is metallic hydrogen. At extreme pressures, hydrogen can transition from a gaseous state to a metallic state, exhibiting conductivity similar to metals. The presence of metallic hydrogen could impact the planet's magnetic field and contribute to unusual atmospheric dynamics, especially in terms of electrical phenomena or the generation of storms. Additionally, the interactions of various gases could lead to the formation of complex compounds or even new types of materials. For instance, ammonia, Methane and other heavy hydrocarbons may interact under the unique conditions present, potentially producing exotic chemical compounds or allowing for the existence of liquid methane lakes or clouds of complex organic materials. The various exotic forms of matter that might exist on Gliese 436b highlight not only the planet's complexity, but also the need to expand our understanding of materials under extreme conditions. By studying these exotic states, scientists can gain valuable insights into both the unique characteristics of Gliese 436b and the fundamental principles that govern matter in diverse environments throughout the universe. Topic: Theia Prime, the planetary collision world. Planetary collisions, such as the one that is theorized to have formed Theia Prime, an early version of Earth, are supported by various pieces of evidence from both simulations and astronomical observations. One compelling aspect comes from computer models of planetary formation, which illustrate how celestial bodies can collide under certain circumstances. These simulations indicate that during the early stages of our solar system, the accumulation of protoplanets was a highly dynamic process, with numerous collisions occurring between these growing masses. Additionally, the lunar surface provides a real-world specimen that bolsters the hypothesis of significant impacts in the past. The Moon's heavily cratered surface showcases a history of violent collisions, including both smaller bodies and larger protoplanets. Through lunar sample analysis, scientists have been able to determine the ages of different craters and correlate this with models of solar system evolution, suggesting that days of intense collisions were not just possible but likely. The detection of exoplanets also adds to our understanding. Many systems exhibit signs of dynamic interactions and collisions among planetary bodies. Observations of these systems have revealed unusual orbital patterns and debris disks that suggest past collisions. Data from telescopes has shown that some planetary systems are chaotic and that collisions can disrupt orbits, leading to configurations that can only be explained through significant impacts. Finally, isotopic analysis of Earth and Moon samples unveils remarkable similarities, indicating a shared origin. Theories surrounding Theia Prime suggest a colossal impact between a Mars-sized body and the early Earth, which would have resulted in the formation of debris that eventually coalesced into the Moon. This aligns with the evidence of widespread energetic collisions in the early solar system as our planets were forming, further supporting the idea that such planetary collisions are an integral part of cosmic evolution. In the immediate aftermath of a colossal collision that formed Theia Prime, the surface would be an arena of chaos and turmoil. Imagine a landscape dominated by superheated rock and molten material, swirling in a haze of dust and vapor. The intensity of the impact would shatter the surface, causing massive upheaval and creating gigantic fissures and craters. Initially, these features would be vast and incomprehensibly deep, carving into the landscape like an artist's scarring brushstrokes on the canvas of a chaotic world. The atmosphere would be dense with debris, obscuring the sky and filling it with a blinding mix of particles and gases. This turbulent atmosphere would consist predominantly of steam and volcanic gases expelled by the violence of the impact, leading to temperatures soaring far beyond what we consider normal for a planetary surface. Over time, as this atmosphere thinned, it would create a harsh, searing environment, with temperatures fluctuating dramatically, contributing to the instability of the surface conditions. As the molten rock began to cool, a new crust would slowly form. However, this would not be a uniform surface. Instead, it would be marred by the remnants of the impact, with irregularities caused by subsequent volcanic activity and continuing collisions from leftover debris in orbit. Pockets of lava might still bubble beneath the surface, occasionally breaking out in fiery displays. During this tumultuous period, the interplay of gravitational forces would lead to further changes. Large bodies of debris from both Theia and Earth would orbit together before either crashing down or merging into different formations. The remnants of this violent encounter would contribute to the raw and rugged terrain, shaping a world destined to evolve into what we now know as Earth, setting the stage for future development of a more stable environment. A planet engaged in active collisions would experience a highly unstable atmosphere if it had one at all. In the throes of such cataclysmic events, the sheer energy released during impacts could strip away any existing atmosphere or significantly alter its composition. The immediate aftermath of a collision would generate intense heat, resulting in the melting of surface materials and the vaporization of significant quantities of rock. This would create a temporary atmosphere filled with superheated gases and vapor, predominantly made up of steam, carbon dioxide, and various other volatile compounds released from the planet's crust. As new impacts occur, this atmosphere would continually be replenished and modified. Each collision can generate shock waves that send debris and gases soaring into the surrounding space, leading to a dynamic atmosphere that changes rapidly. If the planet does retain some atmospheric integrity, the combination of heat and debris would likely lead to high-pressure conditions. These heightened pressures could trap gases, potentially allowing for a thick, toxic environment that is far from hospitable for life as we know it. The presence of such a turbulent atmosphere would also be marked by frequent weather phenomena driven by extreme temperature fluctuations. Thunderstorms fueled by the heat of ongoing volcanic eruptions could dominate, accompanied by intense winds that whip through the thick clouds of gas and grime. Sunlight would struggle to penetrate this murky shroud, and visibility would be severely limited. Over time, the ongoing cycle of collisions and atmospheric changes could lead to different states, depending on how frequently impacts occur and the size of the colliding bodies. In some scenarios, if a planet manages to stabilize, it could eventually develop a more temperate atmosphere as surface conditions normalize. However, while active collisions persist, the atmosphere would remain a fierce and unpredictable environment, reflecting the violence and chaos of its surroundings. As two astronomical bodies approach and begin to merge, the behavior of gravity becomes increasingly complex and dynamic. Initially, gravity acts as the primary force attracting the two bodies together. The gravitational pull between the larger body, such as a planet, and a smaller one, like an asteroid or a smaller planet, grows more intense as they near each other. This escalating gravitational interaction creates tidal forces that produce noticeable distortions in the surfaces of both bodies, leading to bulges and extensions in their shapes. As the two bodies collide, the gravitational forces can cause significant variations in gravity across the surface. Near the point of impact, gravity would be extraordinarily strong due to the immense mass concentrated there, while regions farther away would experience less gravitational pull. This can lead to interesting phenomena such as debris being flung outward because of the sharp changes in gravitational force. The chaotic environment would not only affect the immediate area around the impact site, but could also cause a reconfiguration of orbits for nearby moons or other celestial objects that may be within gravitational reach. Another fascinating aspect arises when one body starts to break apart due to the intense gravitational forces. If the merging bodies are significantly different in size, the smaller body may disintegrate upon impact, resulting in fragments that would also be influenced by the gravity of the larger body. These fragments could enter temporary orbits around the larger mass and experience gravitational interactions that pull them toward the surface or propel them further into space, creating a turbulent environment of shifting masses. As the merging progresses, gravity would play a role in redistributing material from both bodies. The intense pressure and heat generated during the collision could lead to melting and mixing, as gravity pulls materials toward the center of the newly forming mass. Over time, as the two bodies coalesce and the environment stabilizes, gravity would work to create a new, singular body, possessing properties influenced by the remnants of both original bodies. This chaotic interplay of gravitational forces during such a monumental event highlights the essential role gravity plays in shaping celestial formations within our universe. From the surface of Theia Prime during the collision process, the sky would present a breathtaking yet terrifying spectacle. Before the impact, as two massive bodies draw closer, the sky would be dominated by the ominous silhouette of the approaching colliding body. Depending on its size, this object might fill a substantial part of the firmament, casting a shadow across the landscape and invoking an eerie twilight effect even during the day. You would likely witness a dramatic and often turbulent atmosphere, filled with swirling clouds disrupted by shock waves and other atmospheric disturbances. As the collision event escalates, the sky would likely be a kaleidoscope of colors due to the intense heat and gases released from the surface and the interactions with the approaching body. Bright flashes of light might punctuate the clouds as fiery debris is ejected from impacts, illuminating the surroundings in brief bursts of brilliance. The atmospheric disturbances would produce vivid storms and lightning, resulting in a cacophony of colors like deep reds, oranges, and yellows against the darker backdrop created by billowing clouds of ash and vapor. With each moment leading up to the impact, the sky would become increasingly chaotic. Thick plumes of smoke and vapor would rise from the surface, blurring lines of sight and shrouding parts of the sky. The resulting atmospheric pressures would create layers of clouds with lower, dense formations hugging the surface, while higher layers, perhaps charged with electricity, would rumble ominously. The sounds of the collision could amplify this scenario, with echoes of distant impacts reverberating across the landscape. Finally, just before impact, a brilliant flash might light up the sky as the smaller body collides with Theia Prime, releasing energy equivalent to countless nuclear explosions. This moment would not only light up the entire sky, but would also mark the beginning of a new chapter in the planet's formation, forever changing its surface and atmosphere. The appearance of the sky during this tumultuous interaction reflects both the beauty and devastation inherent in cosmic collisions, encapsulating the raw power of the universe at play. The collision and merger process of two planetary bodies, such as Theia Prime and another mass, can span a significant time frame, typically ranging from several hours to even days. This duration is influenced by factors like the size and speed of the colliding bodies, as well as their gravitational fields. The event can be divided into distinct stages, each marked by unique characteristics and processes. In the initial stage, termed the approach phase, the two bodies would draw closer to one another, with their gravitational fields influencing each other's shapes. This phase could last from hours to weeks, depending on their relative velocities. As they enter closer proximity, tidal forces begin to stretch and distort their surfaces, creating bulges that signal the impending impact. The sky would exhibit dramatic phenomena, such as increasing atmospheric disturbances caused by the gravitational interactions. The following stage is the collision itself, where the two bodies come together. This moment is characterized by the release of immense energy, leading to shock waves that ripple through both masses. The impacts would produce vast craters and eject material into the atmosphere, forming plumes of debris. This pivotal moment may occur quickly, but carries devastating consequences, as it marks the transition from separate entities to a combined mass. After the collision, the merger stage commences. During this stage, the debris from the collision begins to coalesce under the influence of gravity, while the heat generated from the impacts leads to melting and mixing of materials. This stage can last days or even weeks as the two bodies gradually reconcile and settle into a more stable configuration. The newly formed mass would experience intense volcanic activity, providing heat and facilitating the eventual formation of a crust. Over time, as conditions stabilize, this process will lead to the formation of a singular planetary body, paving the way for eventual cooling, crust formation, and the development of an atmosphere. Through this transformative journey, the merging process reshapes the landscape and fundamentally alters the cosmic fabric in which these celestial bodies exist, providing a glimpse into the dynamic nature of planetary formation and evolution. During and after the collision that formed Theia Prime, the geological activity would be nothing short of extreme. Initially, the impact event itself would unleash tremendous energy, likely causing widespread melting of rock and generation of massive shock waves that radiate through the planet's crust. This would result in powerful earthquakes, capable of reshaping the surface within moments. These seismic activities could lead to the rapid formation of new geological features, such as giant fissures, craters, and mountain ranges, as the crust responds to the stress imposed by the massive impact. As the collision progresses, intense volcanic activity would dominate the landscape. The heat and pressure generated from the impacts would trigger widespread melting of both planetary bodies. This molten material would rise to the surface in the form of lava flows, eruptions, and pyroclastic flows. Volcanic eruptions could be extraordinarily violent, ejecting ash and gas into the atmosphere, contributing to a thick cloud cover that would again alter the climate and surface conditions on Theia Prime. The landscape would be constantly reshaped as new landforms emerged from eruptive processes. Following the initial impact and volcanic activity, the geological processes would not settle quickly. Instead, the newly formed body would continue to experience tectonic activity shaped by the ongoing gravitational interactions and residual heat from the impact. Mantle convection would be intense, leading to tectonic movements and further volcanic eruptions. The effects of gravity would keep reshaping the surface materials, leading to the formation of a diverse range of geological features, including valleys, plateaus, and potentially even crater lakes, as depressions formed from impacts filled with molten rock. Over time, as Theia Prime began to cool and stabilize, geological activity would persist, but at a reduced scale. However, the legacy of the violent past would remain visible in the form of rugged terrain, a patchwork of volcanic landforms, and a potentially differentiated interior structure that reflects the chaotic processes involved in its merger. This extreme geologic activity underscores the dynamic nature of planetary formation, highlighting how such violent events can profoundly influence a planet's landscape and geological history. The collision between two large planetary bodies, such as Theia Prime and another mass, would have significant repercussions on any moons or nearby planets within the same solar system. The violent nature of such an event would lead to powerful gravitational disturbances, resulting in a complex chain reaction that could affect celestial bodies far beyond the immediate vicinity of the impact. Moons orbiting Theia Prime would experience dramatic changes as gravitational forces fluctuated during the collision. Depending on their proximity, these moons could be subjected to intense tidal forces, leading to shifts in their orbits or, in extreme cases, complete disintegration. If the collision generates debris, this material could be cast into space, potentially forming a ring system or contributing to already existing debris fields. Some of this debris might gravitationally attract nearby moons, causing them to collide or undergo chaotic interactions. For nearby planets, the aftermath of such a monumental collision could lead to alterations in their orbits as well. The sudden release of energy and mass ejected during the impact would create gravitational waves that could disturb other celestial bodies in the solar system. For example, planets in close proximity could find their orbits perturbed or become subject to increased bombardment from debris resulting from the collision. Smaller bodies that might already be in the asteroid belt could also experience changes in their paths, leading to more collisions and further disruptions. In addition to physical interactions, the collision could influence the atmospheres and climates of nearby celestial bodies. The ejected material could enter the atmospheres of moons or planets, changing their compositions. If any of these bodies have atmospheres suitable for life, the sudden influx of debris, gases, and particles could have catastrophic consequences, altering or even obliterating existing ecosystems. Ultimately, the collision would set off a domino effect throughout the solar system, demonstrating how interconnected celestial bodies are and highlighting the complexities of gravitational interactions. The ripple effects would underline the dynamic and often chaotic nature of planetary systems, where events on one body can have profound and lasting impacts on others. Studying theoretical planets like Theia Prime provides invaluable insights into the processes that governed the formation of Earth and its moon. Much of our understanding of these origins revolves around the idea that large-scale impacts played a crucial role in shaping planetary systems. The hypothesis that Theia, a Mars-sized body, collided with the early Earth is central to the giant impact theory, which suggests that such colossal collisions are not only possible, but likely in the turbulent environment of the early solar system. One significant aspect revealed through modeling planets like Theia Prime is the dynamics of planetary accretion. These models display how debris from a violent collision could coalesce to form a moon, as is believed to have happened with Earth's moon. Analyzing various simulations helps scientists identify the specific conditions and characteristics needed for a successful merger that would lead to a stable orbit and form a body like the moon. This understanding sheds light on the particular trajectories, sizes, and compositions necessary to create such celestial relationships. Moreover, theoretical studies allow researchers to explore diverse scenarios concerning the composition and chemistry of both Earth and Theia Prime. Isotopic analyses of lunar samples show striking similarities with terrestrial rocks, suggesting they share a common origin. By examining the potential makeup of Theia, scientists can piece together the conditions that would have been necessary for such matches to occur. The study of hypothetical bodies helps refine our ideas about the materials and processes involved in planetary formation, including the roles of metal, rock, and volatile compounds. In addition, these investigations highlight the importance of understanding impact dynamics beyond Earth and its moon. By extending our focus to other celestial bodies and their moons in the solar system, researchers gain broader knowledge of formation histories among planets. This knowledge greatly enriches our comprehension of planetary evolution and the behaviors of systems similar to our own, ultimately providing a clearer picture of our place within the cosmos. The study of theoretical planets exemplifies how examining the past informs our understanding of present conditions and future possibilities for planets both within our solar system and beyond. If life existed on either of the colliding planets, the effects of such a monumental event would be catastrophic, but not necessarily wholly destructive. The immediate impact of a collision would likely produce extreme heat, shock waves, and widespread environmental upheaval, creating conditions that would be hostile to most known forms of life. The intense energy released could obliterate surface ecosystems, vaporizing water and turning biospheres into inhospitable landscapes dominated by molten rock and ash. However, the potential for life to survive would depend heavily on the characteristics of the organisms and their environments. For example, extremophiles are microorganisms that can endure extreme conditions, such as high heat, pressure, and radiation. If such resilient forms of life existed on one of the bodies, they might be able to withstand the initial surge of heat and could enter dormancy to survive the subsequent upheaval. These organisms could potentially remain sheltered within deep subsurface environments or hydrothermal vents, where the impact's destructive forces would be less severe, providing a refuge from immediate hazards. Furthermore, if any organisms managed to be buried by ejecta, material blasted from the surface during the impact, they could find a semblance of stability. This packed material might insulate them from the harsh surface conditions and allow them to endure until conditions began to stabilize. These organisms could then re-emerge as the environment cooled and reformed, possibly adapting to the new conditions that emerged following the volatile upheaval. The post-collision landscape would initially be rife with opportunities for colonization, as the newly formed landforms and volcanic activity could create niches rich in minerals and other resources. Eventually, once the surface cooled and some degree of stability returned, it might allow for the re-establishment of ecosystems. The remnants of life that survived could evolve and diversify in response to the new environmental conditions shaped by the impact. Thus, while the collision would dramatically alter the landscape and ecology of both planetary bodies, the potential for life to persist and adapt hinges on their resilience, location, and the nature of their environments. Studying such possibilities expands our understanding of life's tenacity and its potential to emerge even in the most extreme circumstances across the cosmos. Supercritical water is a unique state of water that occurs when it is subjected to high temperatures and pressures, specifically above its critical point, which is approximately 371 degrees Celsius and around 226 atmospheres of pressure. In this state, water exhibits properties that are markedly different from those of normal liquid water. At normal conditions, water exists in three states: solid, liquid, and gas. Normal water has a defined structure with distinct separation between the liquid and vapor phases. However, in the supercritical state, water transcends these boundaries, leading to a homogeneous phase that possesses characteristics of both a liquid and a gas. This means that supercritical water can dissolve non-polar compounds like a gas while still retaining some liquidity properties, making it a powerful solvent. The density of supercritical water is much lower than that of liquid water, but higher than that of water vapor. This unique density allows it to penetrate materials much more easily. Furthermore, supercritical water has a much greater diffusivity, enabling it to dissolve gases and organic materials more effectively than in either the liquid or gaseous states. The result is an environment where chemical reactions occur at accelerated rates, a property that is utilized in various technologies, including organic waste treatment and green chemistry. The differences between supercritical water and normal water have significant implications in industrial applications. For instance, in supercritical water oxidation, organic waste can be effectively processed, converting harmful substances into less hazardous materials. This demonstrates how understanding the properties of supercritical water can lead to innovative solutions for waste management and resource recovery, highlighting its versatility and importance in both environmental science and industrial processes. Oceanus extremis, often used as a hypothetical concept in discussions about extreme planetary environments, maintains a global supercritical water ocean under specific conditions related to temperature, pressure, and the overall composition of the planetary atmosphere. The key factor is that the environment must be situated above the critical point of water, which occurs at approximately 371 degrees Celsius and 226 atmospheres of pressure. To sustain such conditions, a planet or moon would need a significant gravitational field to hold a thick atmosphere capable of maintaining high pressures. This high atmospheric pressure prevents the formation of vapor and allows water to remain in its supercritical state throughout the depths of the ocean. In this scenario, a strong geothermal gradient could also play a critical role, where heat from the planet's interior continuously maintains the necessary temperatures. For example, this could occur through active volcanism or tectonic activity that releases heat from within the planetary crust. The composition of the atmosphere is equally important. An atmosphere rich in greenhouse gases, such as carbon dioxide and methane, would trap heat efficiently, helping to sustain elevated temperatures necessary for supercritical water. This dense atmosphere would minimize heat loss to space, maintaining a stable environment where the conditions required for a global ocean of supercritical water can persist. Additionally, the presence of mineral content and chemical constituents dissolved in the water could influence the behavior of the ocean at this state. Different solutes can alter the temperature and pressure at which supercritical water can exist, potentially allowing for some variations in specific locations within the ocean while still maintaining overall supercritical conditions. By understanding these conditions, scientists can explore how extreme environments might develop on distant exoplanets or moons, offering insights into possible forms of life or unique geochemical processes that could emerge within such extreme oceans. The existence of Oceanus extremis challenges conventional views of habitability and demonstrates the vast diversity of planetary environments that could exist in our universe. The properties of supercritical water would have profound implications for a planet's geology and potential for supporting life. The unique characteristics of supercritical water, including its enhanced solvent capabilities, increased diffusivity, and ability to dissolve a wide range of substances would facilitate numerous geological and chemical processes that could reshape the planet's landscape. Geologically, supercritical water could act as a powerful agent of erosion and mineral transport. Its ability to penetrate rocks would allow it to dissolve minerals more effectively than in regular liquid water, leading to the alteration of rock formations and the creation of new geological features. This process could create unique hydrothermal systems where supercritical water interacts with hot rocks, resulting in the formation of mineral deposits and potentially forming hydrothermal vents. These vents could become hotspots for geological activity, contributing to the development of diverse ecosystems. In terms of potential for life, supercritical water could provide essential conditions for unique biochemical processes. If life existed in such an environment, organisms might evolve to utilize the solvent properties of supercritical water, enabling them to access energy and nutrients locked in geological materials that would otherwise be unavailable. The high temperatures and pressures could drive rapid metabolic processes, possibly leading to the emergence of extremophiles, organisms adapted to thrive in extreme conditions, much like those found in Earth's hydrothermal vent ecosystems. Additionally, the presence of supercritical water could influence the planet's overall climate and atmospheric conditions. If supercritical water were to periodically cycle through different phases, either condensing to form vapor or renewing a liquid state, this could influence surface temperatures, weather patterns, and the distribution of nutrients. Such cycles would create dynamic environments capable of supporting a variety of ecological niches. Overall, the presence of supercritical water could lead to a highly active geological landscape and support specialized ecosystems that challenge our traditional understanding of habitability. By examining the implications of supercritical water, scientists can explore the potential for life in extreme environments, not only on hypothetical planets like Oceanus Extremis, but also in the search for life on icy moons or other celestial bodies within our solar system and beyond. Entering the supercritical ocean of a hypothetical body like Oceanus Extremis would present extreme challenges and dangers for both humans and spacecraft. As one approaches this environment, the conditions surpass the limits of what we experience in our own oceans, leading to severe consequences as soon as contact is made. For a human, the first impact with supercritical water would be catastrophic. The high temperatures, possibly exceeding 371 degrees Celsius, would cause severe burns and immediate physiological distress. Conventional protective suits and life support systems would fail to protect against such extreme heat, making survival impossible. Moreover, the high pressures, in excess of 226 atmospheres, would crush a human body, overwhelming any structural integrity provided by fabric or materials designed for survival. Spacecraft would encounter similarly hazardous conditions upon entry. While spacecraft are engineered to withstand immense variations in temperature and pressure, the extreme environment of supercritical water would exceed design limitations. The materials used in spacecraft construction could not sustain the continuous exposure to high temperatures and intense pressures, leading to structural failure. Components not intended for such environments would rapidly degrade, and any onboard systems meant for monitoring or navigating would become inoperable within moments. Should a spacecraft attempt to descend into Oceanus Extremis, buoyancy would also be an issue. As it reaches the supercritical state, water's density changes significantly, resulting in unpredictable buoyancy forces. The craft could sink rapidly or become subject to alterations in pressure that it cannot withstand, leading to implosion. Without specialized technology capable of handling supercritical pressures and temperatures, any exploration missions would face formidable obstacles. Both humans and conventional spacecraft would find it near impossible to survive or operate within Oceanus Extremis' supercritical ocean. Such extreme environments serve to remind us of the complexities and challenges posed by exploring alien worlds beyond our own, driving the need for advanced technologies and adaptations to pursue research in environments radically different from those on Earth. The transition from normal water to supercritical water occurs at a specific combination of temperature and pressure. In this state, water takes on unique properties, behaving more like a gas yet retaining the density of a liquid. Supercritical water exists above 373 degrees Celsius and above 22 megapascals of pressure. This transformation has significant implications, especially in the context of our planet's atmosphere and environmental processes. One major impact arises from its role in the recycling of nutrients and minerals. In geological settings such as subduction zones where tectonic plates interact, supercritical water can facilitate the transport of essential elements. When water is subjected to extreme pressure and temperature, it can dissolve minerals much more efficiently than in its normal state. This contributes to the formation of geothermal features and can influence volcanic activity, releasing gases into the atmosphere, which can affect climate patterns. Furthermore, supercritical water is involved in the processes of organic matter decomposition and carbon cycling. In natural settings, the behavior of water under drastic conditions influences the rates of oxidation and reduction reactions, contributing to the release or absorption of gases like carbon dioxide and methane. These gases play crucial roles in regulating Earth's temperature and contribute to greenhouse gas concentrations, illustrating how such transformations can indirectly impact climate change. Lastly, there are broader implications for energy systems. Researchers are exploring the use of supercritical water for more efficient energy production. Through processes such as supercritical water gasification, biomass can be converted into energy, presenting potential renewable energy solutions. These advancements could further alter how water interacts with the atmosphere, emphasizing the importance of understanding this extraordinary phase transition, not only in geological terms, but also in a future-driven context of sustainability. On a planet with supercritical water oceans, the weather patterns would be remarkably different from anything we experience on Earth. The unique properties of supercritical water, which combines aspects of both gas and liquid phases, would fundamentally alter atmospheric dynamics, heat transfer, and moisture behavior. As a result, the planet's climate could exhibit extreme and unpredictable weather phenomena. Temperature regulation would be one of the most notable changes. Supercritical water can hold vast amounts of heat compared to normal liquid water. This immense heat capacity would lead to a more uniform temperature distribution across the planet, reducing the stark temperature gradients that typically drive weather systems. The result could be a more stable atmospheric structure, with fewer large-scale storms, but the potential for localized, intense weather events where reactions to changes in pressure or thermal content occur. Additionally, the evaporation and condensation processes would behave differently due to the characteristics of supercritical water. In this state, instead of transitioning from liquid to vapor as we observe with conventional ocean water, the water would maintain a constant state while still allowing for gas-like dynamics. This could lead to mysterious cloud formations and possibly more vigorous precipitation events in the form of dense fog or mist rather than traditional rain. Such changes would create unique ecosystems and influence the biological processes occurring in the atmosphere and on the planet's surface. Finally, the interaction between supercritical water and other atmospheric elements might lead to the emergence of entirely new types of storms. These storms could be characterized by their ability to draw energy directly from the supercritical ocean, potentially leading to unprecedented weather systems unlike anything seen on Earth. There might be violent atmospheric disturbances that create powerful winds, unusual cloud types, and continuous lightning activity, illustrating how the peculiar properties of supercritical water could shape the climate and landscape of this hypothetical planet. Oceanus Extremis, a hypothetical ocean located on planets with extreme conditions, presents formidable challenges to our understanding of habitability. When envisioning such an environment, it is essential to consider the temperature, pressure, and chemical composition that define it. These factors drastically diverge from those associated with life as we know it on Earth, forcing scientists to re-evaluate the conditions necessary for survival. The high temperatures and pressures found in Oceanus extremis can lead to unique biochemical environments that many familiar organisms would find inhospitable. For instance, temperatures might soar well above the threshold for conventional life, which typically flourishes within a narrow range of conditions. Organisms on Earth, especially extremophiles, demonstrate the resilience of life, but their adaptations may still fall short under the extreme conditions of Oceanus extremis. This prompts a crucial question: what forms might life take in such environments, and how might they differ from terrestrial life? Moreover, the chemical makeup of Oceanus extremis will significantly influence its capacity for supporting life. If the ocean is saturated with toxic substances or lacks essential nutrients like oxygen, the potential for metabolically active organisms diminishes. This raises the possibility of life forms that utilize alternative biochemistries, perhaps relying on different solvents or energy sources rather than what we deem necessary. The existence of extremophilic life forms on Earth, such as certain archaea and bacteria that thrive in hydrothermal vents, serves as a tantalizing glimpse into how life might adapt to radically different environments. Exploration of Oceanus extremis thus challenges scientists to expand their definitions of habitability. The presence of liquid water was long touted as a primary criterion for life, yet extreme settings can alter this assumption. The search for extraterrestrial life must now encompass a wider range of possibilities, including environments that defy Earth's conventional wisdom on habitability. Consequently, as we study Oceanus extremis and similar extreme domains, we may find that life is not only possible, but also unique in its persistence and adaptability within the most hostile conditions imaginable. Studying a planet with a supercritical water ocean would require innovative and advanced methods, given the unique conditions that such an environment presents. First and foremost, remote sensing technology would play a vital role. Spacecraft equipped with sophisticated instruments could analyze light reflected from the planet's surface and atmosphere. By measuring various wavelengths, scientists could detect the signatures of different compounds, assess temperature variations, and infer the ocean's state, thereby providing crucial information about the dynamic processes occurring in the supercritical water ocean. In addition to remote sensing, scientists might deploy lander or probe missions designed to survive and operate under extreme conditions. These landers would need to withstand high temperatures and pressures while gathering data on the chemical composition and physical characteristics of the ocean. Equipped with specialized sensors, they could sample the water and analyze its properties directly. This would enhance our understanding of the planet's geology, hydrology, and potential for harboring life. Another promising approach would involve deploying autonomous underwater vehicles. These robotic crafts could explore the depths of the supercritical water ocean, collecting samples and conducting experiments in real time. Their design would need to account for the ocean's unique properties, enabling them to operate effectively without being compromised by the conditions. This method could yield insights into the ocean's behavior, circulation patterns, and interactions with the planet's atmosphere. Lastly, laboratory simulations of supercritical water environments on Earth could provide valuable data for interpretations. By creating experimental setups that mimic the extreme conditions of a supercritical water ocean, scientists can study potential chemical reactions, biological processes, and energy cycles. Insights gained from these experiments would inform the analysis of data collected from missions to the planet, enhancing our understanding of this extreme environment and its implications for habitability and the potential for life beyond our own world. The properties of supercritical water could significantly influence both the formation and evolution of a planet. When present in a planet's interior or surface environment, supercritical water alters the behavior of minerals and rocks, playing a key role in geological processes. Due to its unique characteristics, supercritical water can dissolve and transport various minerals more efficiently than normal water, which leads to the enhancement of chemical reactions. This behavior can prompt the formation of diverse geological features. such as hydrothermal vents or mineral deposits, and impact tectonic activity by facilitating the movement of tectonic plates. Moreover, the heat retention capabilities of supercritical water contribute to a planet's thermal dynamics. By magnifying heat transfer from the planet's core to its surface, supercritical water can affect the planet's geological stability and volcanism. This additional heat can create conditions for frequent volcanic activities, which subsequently alters the landscape and could even influence atmospheric composition. The release of gases from volcanic eruptions, such as carbon dioxide and sulfur dioxide, can reshape the atmosphere, further impacting climate and potentially enriching the conditions necessary for various chemical processes. In terms of evolution, the presence of supercritical water would also play a role in the planet's capacity to sustain or evolve forms of life. Its ability to promote chemical reactions and transport nutrients might lead to the emergence of novel biochemical pathways. Life forms could exploit the unique properties of supercritical water, harnessing energy and materials in ways that terrestrial organisms cannot. This opens up possibilities for biospheres that are vastly different from our own, adapting specifically to thrive within such extreme environments. Additionally, the interactions between supercritical water and other planetary materials could influence the long-term evolution of the planet's geology and climate. This constant cycle of dissolution, transport, and precipitation may create a feedback loop through which geological and atmospheric processes become interlinked. Thus, understanding the role of supercritical water is essential for grasping not just the planet's current state, but also the complex history of its formation and the potential pathways for its future evolution. Studying Oceanus Extremis could yield significant advances in technology and space exploration, informing a range of applications that may transform our approach to understanding other celestial bodies. One promising area is the development of advanced materials and robotics engineered to withstand extreme conditions. The unique properties of supercritical water would necessitate resilient technologies capable of enduring high temperatures and pressures. Insights gained from these studies could lead to the creation of more durable instruments designed for future exploration missions, ultimately enhancing their capabilities and lifespans. Additionally, the exploration of Oceanus Extremis might provide valuable knowledge applicable to resource extraction techniques on other planets or moons. Supercritical water has remarkable solvation properties, allowing it to dissolve various elements and compounds. As we learn more about how to interact with and utilize supercritical water, it may pave the way for innovative extraction processes. This could be particularly useful in environments rich in minerals or energy resources, such as those found on asteroids or the icy moons of the outer solar system. Enhancing our ability to extract resources in extraterrestrial environments could support long-term space missions and habitat construction. Another potential application lies in astrobiology, as the study of habitability conditions in Oceanus Extremis may lead to new insights into life's potential in extreme environments. Understanding how organisms adapt to high-pressure, high-temperature conditions could inform our search for life on other planets, particularly those with subsurface oceans, such as Europa or Enceladus. By identifying the biochemical pathways and survival mechanisms viable in extreme situations, we can refine our models for detecting biosignatures on other celestial bodies. Finally, the knowledge gained from Oceanus Extremis could influence the design and function of closed life support systems for future human exploration of distant worlds. As these systems will need to recycle waste and efficiently manage resources in isolated environments, principles derived from studying supercritical water dynamics can inform innovative approaches to manage water and nutrient cycles, ensuring a sustainable habitation in hostile conditions. The exploration of Oceanus Extremis has the potential to expand our technological capabilities, resource management strategies, and understanding of life, all of which are crucial for the future of space exploration. Magnetar is a type of neutron star with an extremely powerful magnetic field, far exceeding that of ordinary neutron stars. After the immense gravitational collapse of a massive star during a supernova explosion, A neutron star is born, composed mostly of densely packed neutrons. While typical neutron stars have magnetic fields that can be 100 million to 1 billion times stronger than that of Earth, magnetars possess fields that can reach 1,000 trillion times stronger. This extraordinary magnetic force profoundly influences their properties and behavior. The intense magnetic field of a magnetar results in unique phenomena such as powerful bursts of gamma rays and X-rays. These emissions occur due to the magnetar's magnetic field being so strong that it can drive temperature increases and energy releases in the star's surface and outwards into space. This phenomenon contrasts sharply with normal neutron stars, which may exhibit periodic pulsations due to their rotation and not display the same level of electromagnetic violence. Magnetars are often characterized by their sporadic bursts of radiation, making them some of the most energetic objects in the universe. Another fascinating aspect of magnetars is their relatively short lifetimes compared to regular neutron stars. The magnetic fields of magnetars can decay over time, and while normal neutron stars can persist for millions or even billions of years, magnetars might only shine brightly for about 10,000 years before their magnetic fields weaken significantly. This rapid decline not only contributes to their rarity, but also affects the surrounding environment, as their energetic outbursts can influence nearby cosmic materials and potentially trigger star formation. Understanding magnetars provides valuable insights into the fundamental physics of extreme states of matter, magnetic fields, and the life cycle of massive stars. As these celestial bodies challenge our knowledge about the universe's most extreme conditions, their study can also shed light on the mechanisms that govern other astrophysical phenomena, further enriching our understanding of the cosmos. Magnetar 1b, a hypothetical magnetar, would possess an extraordinarily strong magnetic field that could reach strengths on the order of 1,000 trillion Gauss. To put this into perspective, this is several orders of magnitude greater than the magnetic fields found on typical neutron stars and about 100 million times stronger than the fields associated with ordinary neutron stars. By comparison, Earth's magnetic field is relatively weak, measuring around 50 microteslas. In Gauss, this translates to about 0.5 Gauss. When contrasting these figures, the magnetic field of Magnetar 1b dwarfs that of Earth, highlighting an immense difference in strength. The magnetic fields of magnetars are so powerful that they can profoundly affect the behavior of matter and energy in their vicinity, leading to extreme phenomena such as bursts of gamma rays and X-rays. The staggering strength of Magnetar 1b's magnetic field means that it could influence its surroundings in ways that are difficult to comprehend from the standpoint of our own planet's experiences with magnetism. For example, such a powerful field would readily reshape the trajectories of charged particles, drastically altering the conditions in the star's environment and potentially affecting nearby celestial objects. The magnetic field of Magnetar 1b would far surpass Earth's, demonstrating the fierce nature of magnetars in the universe. The study of such extreme magnetic properties not only provides insight into the nature of magnetars themselves, but also contributes to our understanding of cosmic physics in general. The extreme magnetic field of a magnetar, such as Magnetar 1b, would have profound effects on the structure and composition of any planet in its vicinity. One of the most immediate impacts would be felt in the form of intense electromagnetic forces that could influence the arrangement and behavior of materials on the planet's surface and within its atmosphere. The high magnetic field strength would cause charged particles in the atmosphere to become highly ionized, potentially leading to extraordinary phenomena such as auroras far more brilliant than those observed on Earth. At the core of the planet, the magnetic field might significantly affect geological processes, including the behavior of molten metals and mineral formation. If the planet has a metallic core, the influence of the magnetar's magnetic field could lead to unique crystallization patterns or even dictate the types of minerals formed. Materials that are typically stable under normal conditions might behave unpredictably when subjected to such intense magnetic influences, leading to a potentially altered geological composition. Furthermore, the presence of extreme magnetic fields could hinder the development of a standard atmosphere. The interaction between the magnetic field and solar wind from the magnetar could strip away lighter elements, such as hydrogen and helium, leading to a thin or unstable atmosphere. This process could change the planet's ability to support life, as a robust atmosphere is often a critical factor in habitability. Lastly, the radiation emitted from a magnetar, coupled with its intense magnetic field, could also drive chemical reactions in the planet's surface materials that would not typically occur. This could lead to the formation of exotic compounds or changes in the elemental makeup over time. The extreme conditions generated by the magnetar's influence would create a dynamic and evolving environment, contributing to a unique planetary system that deviates significantly from more typical solar systems. The study of such planets opens intriguing questions about the thresholds of life and the adaptability of materials under extreme cosmic conditions. If Magnetar 1b possesses an atmosphere, the interaction between its extreme magnetic field and the atmosphere would lead to a range of fascinating phenomena. The strength of the magnetic field, reaching levels on the order of 1,000 trillion Gauss, would have a dramatic influence on the behavior of charged particles and ions within the atmospheric layer. As these particles interact with the magnetic field, they would spiral along the field lines, leading to complex dynamics that could create unique atmospheric structures. One significant effect would be the enhancement of ionization processes. The intense magnetic field could cause the atoms and molecules in the atmosphere to become ionized, producing a higher concentration of charged particles. This ionization would lead to vivid displays of auroras much more intense and diverse than those seen on Earth, creating dazzling lights that could illuminate the planet's sky in various colors. Such atmospheric phenomena could be a communication medium for any potential life, or could contribute to complex chemical reactions in the atmosphere. Additionally, the magnetic field would interact with the solar wind, a stream of charged particles emanating from the magnetar itself. This interaction could create a unique magnetosphere around the planet, providing some degree of protection against the intense radiation. However, if the atmosphere is thin or composed largely of light gases, the solar wind's pressure could overwhelm the magnetosphere, leading to atmospheric stripping. Over time, this could result in the loss of atmospheric mass, altering the planet's characteristics and potentially making it less hospitable. The interplay between the magnetic field and the atmosphere could also influence weather patterns and climatic conditions on Magnetar 1b. Variations in ion density and structure within the atmosphere might result in unusual weather phenomena, such as charged particle storms or plasma clouds. These factors would combine to create a highly dynamic and energetic atmospheric environment, fundamentally differing from what we experience on Earth. Overall, the interaction of Magnetar 1b's magnetic field with its atmosphere would lead to a fascinating and complex system, affecting everything from atmospheric composition to potential weather patterns. This dynamic interplay would challenge our understanding of atmospheric science and the potential for stable, habitable environments around extreme celestial bodies. As electronic devices or spacecraft approach Magnetar 1b, they would encounter a series of extreme challenges, primarily driven by the magnetar's incredibly powerful magnetic field and intense radiation environment. The magnetic field strength, reaching levels far stronger than anything observed in our solar system, would pose significant risks for electronic circuits and systems. Many standard electronics are not designed to withstand such levels of magnetic interference, which could lead to malfunctions or complete failures of onboard systems. One of the first concerns would be the risk of magnetic induction, wherein the extreme magnetic field could induce currents in electrical components. This phenomenon might create voltage spikes that could damage or disrupt the spacecraft's electronics. Critical systems for navigation, communication, and data processing could be compromised, leaving a spacecraft vulnerable or unable to perform its intended functions. Designing spacecraft to withstand these magnetic influences would require specialized shielding and robust electronics that can endure such harsh conditions. In addition to magnetic interference, the radiation environment surrounding Magnetar 1b would also pose a significant threat to spacecraft. Magnetars emit intense bursts of X-rays and gamma rays that can damage the fabric of materials and electronics. This radiation would necessitate careful design considerations to protect sensitive components. Radiation shielding would be essential, requiring heavy and durable materials that could increase the weight of the spacecraft, impacting its design and efficiency. Furthermore, any spacecraft approaching Magnetar 1b would need to account for gravitational forces. The dense mass of the Magnetar itself would exert a strong gravitational pull, requiring precise calculations for trajectory and maneuvering. Coupled with the Magnetar's environmental hazards, spacecraft would need to be equipped with advanced navigation systems that could handle these complex gravitational interactions. The extreme magnetic field and intense radiation around Magnetar 1b would significantly challenge the design and operation of electronic devices and spacecraft. These elements would require innovative engineering solutions and robust protective measures to ensure safe operations in such an extraordinarily hostile environment. Investigating the interactions and potential adaptations for technology in this context could yield valuable insights for future space exploration missions, especially in extreme astrophysical environments. The extreme magnetic field of Magnetar 1b would pose significant challenges for any potential life forms on or near the planet. As a magnetar produces a magnetic field hundreds of millions of times stronger than Earth's, the resulting environment would create unique conditions that could both hinder and, in some cases, even foster unusual forms of life. One of the most immediate effects on potential life would be the intense ionization of the atmosphere. The extreme magnetic field could lead to an abundance of charged particles, creating a highly energetic environment. This ionization might make the atmosphere hostile to conventional biochemical processes as we know them on Earth. Many organic molecules could be destabilized or broken down by radiation associated with such a strong magnetic field, or by the energetic particles it produces, limiting the types of chemical reactions necessary for life as we understand it. However, this environment could also open the door to the possibility of alternative forms of life that adapt to extreme conditions. Life forms may evolve unique biochemistries capable of surviving high radiation levels and utilizing the available energy from the intense electromagnetic activity. These organisms might harness the energy from the magnetic field itself, much like some extremophiles on Earth that thrive in high radiation environments, such as those found near nuclear reactors. Moreover, if life were to develop in close proximity to Magnetar 1b, it might evolve protective adaptations against the intense magnetic field. For instance, bioluminescence or reflective outer structures could serve as forms of protection from radiation. Alternatively, potential life forms could develop specialized magnetic particles within their cells, similar to magnetotactic bacteria on Earth, which might help them navigate or mitigate the effects of the magnetic environment. On a broader scale, the strong magnetic field may influence the behavior of any microbial communities or multicellular organisms. For example, the presence of charged particles in the atmosphere could give rise to unique atmospheric phenomena that impact the habitats where life could exist. Overall, while the extreme magnetic field surrounding Magnetar 1b presents formidable challenges to the idea of life as we know it, it may also encourage the development of highly specialized life forms that could adapt to and thrive in such extreme and alien environments. On Magnetar 1b, the unique combination of an extreme magnetic field and the potential for energetic emissions would create an array of spectacular phenomena observable both in the sky and on the planet's surface. One of the most striking features would likely be the presence of intense and colorful auroras. These auroras would arise from the interaction between the planet's magnetic field and charged particles originating from the magnetar itself or from solar wind, resulting in brilliant displays of light that could envelop large areas of the atmosphere. Unlike Earth's auroras, which are typically green and red, those on Magnetar 1b could showcase a far broader spectrum of colors due to the diversity of particles involved. In addition to auroras, there could be dramatic atmospheric events resulting from the high levels of ionization. Such conditions might lead to the formation of unique plasma storms or clouds that glow brightly, creating a constantly shifting canvas in the sky. These plasma phenomena would result from the charged particles swirling under the influence of the magnetic field, potentially generating spectacular lightning-like discharges and energetic storms that would be mesmerizing to observe. The surface of Magnetar 1b could also exhibit unique geological features shaped by its harsh environment. If the planet has a solid surface, extreme magnetic forces could lead to unusual mineral formations or patterns that reflect the interaction between geological activity and magnetic processes. The conditions might allow for the existence of exotic compounds not typically found on Earth, resulting in unusual colors and textures on the surface. Furthermore, if there are any life forms present, their interactions with the extreme environment could generate their own visible phenomena. These organisms might exhibit bioluminescence, responding to the intense magnetic field or radiation with glowing patterns. Overall, the sky and surface of Magnetar 1b would offer a breathtaking view of dynamic and extraordinary phenomena, illustrating the compelling interplay of extreme magnetic forces, energetic emissions, and potentially exotic geological and biological activity. Such a planet would undoubtedly present an enchanting spectacle, challenging our understanding of physics and the nature of habitability in the universe. Detecting and studying planets with extreme magnetic fields, such as those surrounding magnetars, involves a range of advanced techniques and instruments tailored to capture the unique signatures these environments exhibit. One of the primary methods utilizes observational astronomy, where astronomers employ telescopes equipped with specialized sensors to observe the electromagnetic spectrum. Instruments tuned to detect radio waves, X-rays, and gamma rays are particularly valuable, as these wavelengths can reveal the energetic processes occurring around magnetars and any planets that may be influenced by their strong magnetic fields. Spectroscopy plays a crucial role in this detection process by analyzing the light from these celestial objects. By studying the absorption and emission lines in the spectrum, scientists can glean information about the chemical composition and physical conditions of the atmosphere surrounding the planet. Variations in these spectral features may indicate the presence of ionized elements or other phenomena caused by extreme magnetic fields, helping researchers to infer surface conditions and potential habitability. Another important method is the use of space missions equipped with magnetometers designed to measure magnetic fields directly. These instruments can detect changes in the magnetic environment and provide insights into a planet's magnetic field strength and structure. By mapping the magnetic field lines and understanding how they interact with the surrounding environment, scientists can deduce the planet's characteristics and better understand the influences of its magnetic field on potential atmospheres and surface conditions. Additionally, studying exoplanets in the context of their host stars can yield insights into their magnetic properties. Observations of flare activity or radiation emitted from the stars allow scientists to assess the impact of extreme environments on nearby planets. This information can be collected through ongoing missions and telescopes focused on exoplanet research, enabling scientists to develop models of how extreme magnetic fields might shape a planet's atmosphere, geology, and potential for hosting life. Overall, the detection and study of planets with extreme magnetic fields require a multifaceted approach that leverages a variety of observational techniques and sophisticated instruments. This field continues to advance through international collaborations and the development of new technologies, increasing our understanding of the dynamics of such fascinating celestial bodies and their environments. Studying Magnetar 1b can provide profound insights into the limits of planetary magnetic fields and the processes that govern magnetic field generation and behavior in extreme environments. One of the primary lessons comes from understanding the effects of an extraordinarily strong magnetic field on a planet's structure, atmosphere, and potential for hosting life. By examining how such a magnetic field interacts with various planetary materials and environmental conditions, scientists can better contextualize the influences of magnetic fields on habitability and atmospheric dynamics. Another important aspect involves the study of magnetic field generation through dynamo processes. Understanding the internal mechanisms that might produce a magnetic field of such extreme strength could reveal new information about the conditions necessary for magnetic field formation in planetary bodies. For example, studying how magnetar 1b generates and maintains its field could shed light on the limits of dynamo theory and the parameters required for sustaining magnetic fields on a planetary scale. Moreover, examining the environmental challenges presented by extreme magnetic fields could help scientists define the thresholds that limit the effectiveness of magnetic fields in protecting planetary atmospheres. For example, it can reveal how incredibly potent magnetic fields might safeguard a planet from external radiation or solar winds, thus preserving its atmosphere and influencing potential habitability. Any insights gained about atmospheric stripping due to magnetic interactions could further our understanding of similar processes affecting planets in our own solar system and beyond. Additionally, investigating Magnetar 1b might lead to the discovery of novel materials and reactions uniquely influenced by extreme magnetic fields. Understanding how these conditions affect mineral formation, chemical processes, and possibly even biological functions can broaden our comprehension of what is necessary for life and how it can adapt under extreme circumstances. Studying Magnetar 1b not only challenges and expands our knowledge about the intricacies of planetary magnetic fields, but also encourages a re-evaluation of our assumptions surrounding habitability, geological processes, and the potential for life in extreme environments. This research could ultimately redefine our understanding of planets throughout the universe, pushing the boundaries of what we consider possible within the realms of planetary science and astrobiology. Magnetar 1b is an extraordinary type of neutron star, known for its incredibly powerful magnetic field, which is several million times stronger than that of an ordinary neutron star. This immense magnetic force is generated by the unusual conditions present in such densely packed celestial objects caused by the collapse of massive stars during supernova events. Over time, this magnetic field can fluctuate in intensity, gradually weakening as the star ages and loses energy. As Magnetar 1b continues to evolve, several factors will influence its magnetic field. The internal dynamics of the neutron star play a significant role, particularly the movement of conductive materials within its core. The intense magnetic field can also contribute to structural changes in the star, affecting how energy is distributed and, consequently, the strength of the field itself. Interestingly, some models suggest that these magnetic fields may even experience bursts or spikes of activity, leading to temporary increases in their intensity. The long-term fate of Magnetar 1b is equally fascinating. Eventually, after millions of years, the star is likely to transition from being a magnetar to a regular neutron star as its magnetic field dissipates. As this occurs, it will also cool down considerably, losing the high-energy emissions that characterize magnetars. This cooling process could result in a more stable state, but the remnants of its once formidable magnetic presence will leave an imprint, influencing the surrounding environment. Ultimately, Magnetar 1b, like its stellar brethren, will face a gradual end. It may one day cool to the point where it no longer exhibits any active characteristics. This transformation reflects the life cycle of cosmic objects, illustrating how even the most extreme entities in the universe evolve and change over vast stretches of time. The fascinating dynamics of Magnetar 1b's magnetic field serve as a reminder of the complexity and wonder of our universe. Chronos flux is a hypothetical concept rooted in advanced theories of cosmology, specifically in the study of properties that influence the passage of time. One of the primary features of Chronos flux is its association with the gravitational field and the expansion of space-time itself. According to the theory of relativity, time flows differently in varying gravitational environments, and Chronos flux could amplify these effects, leading to significant time dilation. Near a source of intense gravity, such as a black hole or a densely packed celestial body, time is observed to slow down relative to regions of weaker gravity. This phenomenon occurs because the curvature of space-time caused by massive objects affects the flow of time. Chronos flux could play a role in amplifying this gravitational influence, creating even greater disparities in the passage of time for observers in different locations. Another important aspect of Chronos flux is its potential interaction with velocity. As an object approaches the speed of light, time for that object accelerates more slowly compared to a stationary observer. This time dilation effect is a fundamental aspect of Einstein's theory of special relativity. Chronos flux could enhance this interaction, resulting in more pronounced differences in time experience based on the relative speeds of observing entities. Additionally, if Chronos flux were to involve exotic matter or unusual energy states, it might alter the usual behaviors expected from both gravity and velocity, pushing the boundaries of time dilation even further. The intricate relationship between time, space, and the properties of Chronos flux continues to intrigue scientists and cosmologists, raising profound questions about the nature of time itself and our understanding of the universe. On the surface of Chronos flux, the passage of time would be significantly different than what we experience on Earth due to extreme gravitational or energetic conditions. This difference arises from the principles outlined in Einstein's theories of relativity. According to general relativity, the stronger the gravitational field, the slower time passes. If Chronos flux exerts an intense gravitational influence or involves unique characteristics that warp space-time, we would witness dramatic time dilation effects. For someone on the surface of Chronos flux, time would move more slowly compared to an observer on Earth. This means that while only a short duration might pass for them, maybe just a few minutes or hours, a much longer duration could be occurring on Earth, perhaps days or even years. This disparity creates an intriguing scenario where the inhabitants of Chronos flux could essentially experience a form of time travel into the future compared to those remaining on Earth. Additionally, if the surface of Chronos flux interacts with high-velocity elements or involves phenomena like extreme cosmic forces, these factors could compound the effects of time dilation. For example, if an object were to be moving at speeds approaching that of light on Chronos flux, the rates of time experienced would be dramatically altered. This could result in scenarios where someone traveling to Chronos flux returns to find that significantly more time has elapsed on Earth than they experienced.